Astronomers have been trying to find the answer to a seemingly simple question for more than 100 years. How big is our galaxy? Earth can't go outside the Milky Way to get a straight reading of it. As if we were trying to make a map of a forest while standing between the trees, every observation we make is from inside the structure we're trying to map. Scientists have finally made the most exact map of our home galaxy thanks to new information from radio telescopes, Gaia's billion-star study, and X-ray satellites that scanned the invisible halo. They discovered that the Milky Way is a lot bigger, heavy, and more complicated than anyone thought. The challenge of measuring a galaxy from the inside. As an example, try to describe the shape of your home while you're in the middle of one of its rooms. Some walls, the roof, and maybe some windows can be seen, but the whole layout is still covered. That's the issue scientists have when they look at the Milky Way. Our galaxy is right here where we live, so we can see and measure it. Every telescope on Earth, every camera in space, and every signal we pick up comes from somewhere inside the galactic disk. We can't go outside and take a picture of our house from far away. This single fact explains why the Milky Way's true size has remained one of astronomy's most persistent mysteries. For galaxies millions of light years away, astronomers can simply point a telescope and measure their apparent diameter. But for our own galaxy, that perspective doesn't exist. From Earth's location, about 26,000 light-years from the center, we're buried in a dense layer of dust and stars that block most of the view. The galactic plane is filled with gas, dark nebulae, and clusters of stars whose light overlaps and scatters. Even with powerful telescopes, visible light can travel only a few thousand light-years before being absorbed. Beyond that, the Milky Way becomes an opaque fog. Early astronomers tried to estimate the galaxy's dimensions by counting stars in every direction. In the 18th century, the British astronomer William Herschel conducted one of the first systematic surveys. He assumed that the number of stars visible in a given direction indicated the thickness of the galaxy along that line of sight. His map looked impressive for its time, a flattened, roughly oval island of stars with the sun at its center. But it was completely wrong. The problem wasn't his logic, it was the dust. The interstellar medium hid most of the distant stars from view, giving the false impression that the galaxy ended just beyond what he could see. For decades, this misconception shaped our understanding of the universe. Many believed the Milky Way was the entire cosmos, a finite collection of stars surrounded by darkness. Only in the early 20th century did astronomers begin to realize that our galaxy is just one among billions, and even within that revelation, its true boundaries remained uncertain. Every new telescope and wavelength brought another layer of complexity. Optical surveys showed bright stars, but not the faint background. Radio telescopes revealed cold hydrogen clouds but couldn't pinpoint precise distances. Infrared observatories saw through dust but introduced new distortions in scale. Each method solved one problem while creating another. Another major obstacle is distance measurement itself. Knowing where something lies in three-dimensional space requires accurate distance data, not just direction. The night sky is like a flat projection, a dome of light with no depth. To build a 3D map, astronomers needed to measure how far each object truly was. That required parallax measurements, tiny shifts in a star's apparent position as Earth orbits the Sun. But even with modern instruments, parallax angles for distant stars are so small that they're measured in thousandths of an arcsecond. For comparison, that's like detecting the width of a coin on the Moon from Earth. Until recently, this limitation confined our accurate distance data to a relatively small region around the Sun. Everything beyond that was guesswork. Astronomers relied on indirect indicators, such as the brightness of Cepheid variable stars, to estimate how far certain regions might be. These approximations were enough to reveal the general spiral shape of the Milky Way, but not its true size. The farther out you go, the less reliable those estimates become. The fact that the galaxy spins makes things even harder. You can't just watch the Milky Way, it spins, From where we are, the spin changes how we see distance and speed. Stars closer to the center circle faster than stars farther away. From inside the disk, the spiral arms meet, speeds blur, and light is either moved red or blue depending on its direction. Before astronomers can make a real measurement, they have to figure out how to fix all of these problems. It's not easy to answer the question of where the galaxy ends. A galaxy doesn't have a sharp edge like a planet or moon does. It slowly loses its light, its gas thins out, and its stars become fewer and farther between. It depends on what you're measuring to decide what the edge is. The space between the stars could be 120,000 light-years. The space between the gas and dark matter could be 200,000 light-years, and the space between them could be 2 million. There is more than one right answer, and they are all exactly correct. From early estimates to modern precision. The process of figuring out how big the Milky Way is starts with guessing and ends with math that is so accurate that it can track the movements of individual stars. Astronomers have only been able to guess about the galaxy's size for hundreds of years. They thought that the bright band of light that stretched across the night sky must have been the limits of the universe. That idea ruled science until better tools and more in-depth reasoning showed how incredibly wrong it was. In the 1700s, when William Herschel tried to map the Milky Way by counting stars in every direction, the result seemed convincing: a flat, disc-like shape centered on the sun. His method was simple but flawed. The more stars he saw in a particular direction, the farther he thought the galaxy extended that way. Unfortunately, dust clouds blocked his view in most directions, and his telescope could only detect relatively bright stars. The universe, as seen through his instrument, appeared limited and symmetrical. Herschel had unknowingly drawn a galaxy only a few thousand light-years across, with the sun sitting neatly at its center. A century later, new telescopes with better optics expanded that view, yet confusion remained. Astronomers began to notice spiral nebulae, faint swirling clouds scattered beyond the Milky Way's edge. Some believed these were distant galaxies, while others insisted they were smaller gas formations within our own. The debate came to a head in 1920 during what became known as the Great Debate between Harlow Shappley and Heber Curtis. Shappley argued that the Milky Way was vast, hundreds of thousands of light-years wide, and contained everything. Curtis disagreed, claiming the spiral nebulae were independent galaxies far beyond ours. Both men were partially right, but the decisive proof came soon after. In 1923, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to identify Cepheid variable stars inside the Andromeda Nebula. These stars pulse in brightness at predictable rates, and their periods reveal their absolute luminosity. By comparing how bright they appear to how bright they should be, astronomers can calculate their distance. Hubble's data proved that Andromeda was over 2 million light-years away, far beyond the Milky Way. Overnight, the universe expanded from one galaxy to billions. This discovery didn't answer the question of how big the Milky Way is right away, but it did help scientists understand it better. They now knew that our galaxy was just one of many, and they could look at other galaxies and see how their features were different from ours. In the 1930s and 1940s, astronomers used star counts and variable stars to figure out that the Milky Way was about 100,000 light-years across. This number stayed surprisingly fixed for decades, but that picture only showed the part of the galaxy that could be seen, which was full of bright stars and gas. Radio astronomy changed everything. After World War II, scientists began detecting the faint 21-centimeter emission line produced by neutral hydrogen atoms. This radio signal penetrates interstellar dust that blocks visible light. When astronomers tuned their radio telescopes to that wavelength, they saw something new: a continuous distribution of gas far beyond the optical edge. The Milky Way was not just 100,000 light-years wide. Its gas disk extended more than twice that distance. Radio mapping revealed spiral arms invisible to optical telescopes and regions of dense gas waiting to form new stars. As technology improved, The next revolution came from space-based observatories. Infrared missions such as COBE and Spitzer could see through dust and measure stellar populations hidden from view. Their data showed that the Milky Way's disk wasn't a clean circle, but an uneven, warped structure. In some directions, the outer rim dipped downward. In others, it arched upward, distorted by gravitational interactions with nearby dwarf galaxies and the pull of dark matter. These observations forced astronomers to abandon the idea of a simple flat disk. Then came the European Space Agency's Gaia mission, launched in 2013. Gaia's instruments measure the positions, motions, and brightness of over 1 billion stars, an unprecedented dataset. For the first time, astronomers could construct a three-dimensional model of the Milky Way with precise distances rather than estimates. The results shocked even professionals. Stars once thought to mark the edge of the disk turned out to be only halfway out. Others, barely visible in earlier surveys, lay far beyond, revealing that the galaxy stretched well past 120,000 light-years in stellar extent, with gaseous and dark matter components reaching several times farther. By combining Gaia's stellar data with radio, infrared, and X-ray observations, astronomers have created a layered map of the Milky Way, one that includes its luminous core, its diffuse halo, and the vast faint gas clouds that envelop it. Each wavelength tells a different story. Optical light shows the stars. Radio waves reveal the cold hydrogen between them. Infrared exposes dust-shrouded regions where new stars are born. X-rays highlight the hot, million-degree gas halo that encases the galaxy. Together, they paint a picture of a structure far grander and more complex than the old textbook diagrams suggested. According to modern figures, the Milky Way's stellar width is between 120,000 and 150,000 light-years. Its gas disk is about 200,000 light-years across, and its unseen dark matter halo is about 2 million light-years across. It's 1 trillion times heavier than the Sun as a whole. Still, every new piece of technology seems to make it bigger. With each new generation of devices, the limits are pushed further, revealing more stars, gas, and gravitational pull. Stellar parallax and the cosmic distance ladder. There is one thing that every picture of the Milky Way needs to know: how far away each star is. Even the most beautiful star charts are useless without exact distances. There may be hundreds of light-years between two stars that look like they are next to each other in the sky. Stellar parallax, one of the most clever methods in astronomy, was used to solve this problem. Parallax is the apparent shift in an object's position when viewed from two different angles. You can test it by holding up your finger and alternately closing one eye, then the other. Against the background, your finger seems to jump slightly side to side. The same principle applies to stars. As Earth orbits the Sun, our perspective changes, and nearby stars appear to move slightly against the more distant background. That tiny movement, the parallax angle, becomes the first rung on the cosmic distance ladder. The concept dates back to the ancient Greeks, but the shift was far too small for their instruments to detect. The first successful measurement came in 1838, when Friedrich Bessel used a heliometer to measure the parallax of the star 61 Cygni. He calculated that the star lay about 10 light-years away, a groundbreaking achievement that gave humanity its first direct measure of stellar distance. For the first time, the scale of space became real. Still, parallax has its limits. It seems like a star's shift gets smaller as it gets farther away. The angle is so small, beyond a few hundred light-years, that not even the best telescopes on Earth can see it clearly. Astronomers needed more ways to reach the other side of the galaxy. These ways are built on top of each other to make what is called the cosmic distance ladder. The next step came from variable stars, specifically Cepheid variables. These are giant stars that expand and contract in predictable cycles, causing their brightness to fluctuate rhythmically. In 1908, Henrietta Swan Leavitt discovered that the period of a Cepheids pulsation directly correlates with its intrinsic luminosity. The slower it pulses, the brighter it truly is. This discovery was revolutionary. By observing a Cepheids pulsation rate and comparing its true brightness to its apparent brightness, astronomers could calculate its distance. Suddenly, stars and clusters thousands of light years away became measurable. Cepheids soon became the standard candles of galactic measurement. Their predictable behavior allowed astronomers to chart large portions of the Milky Way's spiral arms and later even determine the distance to other galaxies. But for mapping the Milky Way's structure in fine detail, Cepheids weren't enough. The galaxy contains billions of stars, most of which are too faint or too stable to serve as standard candles. That's where newer parallax missions came in. In 1989, the European Space Agency launched Hipparcos, the first space telescope dedicated to measuring stellar positions without the distortion of Earth's atmosphere. Hipparcos measured parallaxes for over 100,000 stars with unprecedented precision, extending our accurate reach across hundreds of light years. Yet the real breakthrough arrived in 2013 with Gaia. Gaia's instruments are so sensitive that they can detect parallax shifts smaller than 1/100th of a millisecond, equivalent to measuring the width of a human hair from 1,000 kilometers away. Using this capability, Gaia has mapped the positions, distances, and motions of more than 1 billion stars, creating a three-dimensional atlas of the Milky Way. Each new data release adds billions of measurements, refining our understanding of the galaxy's true structure. Through Gaia's data, astronomers can trace the spiral arms, measure the warp of the galactic disk, and even identify streams of stars from galaxies long ago absorbed by the Milky Way. More importantly, they can calibrate the other rungs of the cosmic distance ladder. The parallax distances. Gaia provides anchor the accuracy of Cepheids, RR Lyrae stars, and Type Ia supernovae, which in turn measure distances to faraway galaxies. This interconnected framework allows scientists to move step by step from our solar neighborhood to the edge of the observable universe, all starting with the slight wobble of a nearby star. The results have changed everything. Astronomers are more sure than ever that they have found the Milky Way's exact size, thanks to direct parallax data from stars thousands of light years away. Gaia has shown that the Sun doesn't sit in a completely flat disk, but in a part of the Orion arm that is slightly curved. In its path, it has found the width of the galactic plane, the tilt of the galaxy's edge, and even the motion of stars that circle the edge. We can now see the Milky Way as a live, changing structure instead of a still background for the first time. Even Gaia cannot see everything. Beyond its limit, tens of thousands of light years, astronomers must rely again on indirect indicators: brightness, color, and spectral signatures. They compare these with nearby calibrations from parallax data, climbing the ladder one step at a time until distances to the galaxy's outer regions emerge. This chain of measurements, built from overlapping techniques, is what turns scattered points of light into a measurable galactic map. Neutral hydrogen and the 21-centimeter revolution. By the middle of the 20th century, scientists had learned how to accurately map close star clusters and stars, but they could still not see large parts of the Milky Way. Most visual light was covered by dust clouds, so even the most powerful telescopes could only see a small part of how our galaxy really is put together. It wasn't a bigger lens that made the next big step forward. It was a different kind of light. Radio astronomy was the big step forward, and the finding of a single faint band, 21 centimeters, was its defining moment. This 21-centimeter signal originates from one of the most abundant substances in the universe, neutral hydrogen. Each hydrogen atom consists of one proton and one electron. In rare cases, the spins of these two particles flip relative to each other, releasing an extremely low-energy photon with a wavelength of 21 centimeters, or a frequency of about 1,420 megahertz. This is an emission line so weak that it was only theoretical until the 1940s, when Dutch astronomer Hendrik van der Hulst predicted it as a way to detect hydrogen in deep space. In 1951, radio astronomers in the United States and the Netherlands finally detected it. The impact was immediate. Unlike visible light, radio waves pass easily through interstellar dust. That meant scientists could suddenly see hydrogen gas across the entire galaxy. Because hydrogen is the main ingredient of interstellar space, mapping its 21-centimeter emission revealed the Milky Way's full structure in a way that optical telescopes never could. For the first time, astronomers were not limited by the dark lanes of dust that crisscrossed the galactic plane. They could peer straight through it, measuring not just the position of gas clouds but also their motion. Here's how. When a hydrogen cloud emits its 21-centimeter signal, the light is shifted slightly in frequency, depending on whether the cloud is moving toward or away from us. This shift, the Doppler effect, lets astronomers measure the cloud's velocity relative to Earth. By combining these velocity measurements with our knowledge of the galaxy's rotation, they can determine how far away each cloud lies. In essence, radio astronomers turned the Milky Way into a vast laboratory for studying motion and structure on a galactic scale. Within a few years of the discovery, teams around the world began assembling the first radio maps of the Milky Way. Observatories in Australia, the Netherlands, and the United States worked together to trace hydrogen throughout the sky. The results revealed a spiral structure stretching far beyond the regions visible in optical light. It became clear that our galaxy is a grand spiral system with multiple arms, something that earlier star counts had only hinted at. These early radio surveys also extended the known size of the galaxy. Before 1951, most astronomers thought the Milky Way's disk spanned perhaps 80,000 to 100,000 light-years. But 21-centimeter data showed that hydrogen clouds continue far beyond that limit, well past the outermost stars visible in optical surveys. In some directions, the gas extended more than 150,000 light-years from the center, and faint traces reached even farther. The galaxy, once imagined as a thin island of stars, turned out to be surrounded by a vast, diffuse sea of hydrogen. The galaxy's spin shape was another important discovery. It was possible to see how orbital speed changes with radius by tracking how fast hydrogen clouds move at different distances from the center. Newtonian physics says that the galaxy's edges should spin more slowly, just like planets that are farther from the Sun move more slowly. The numbers didn't show that, though. Instead, the speed of spin stayed pretty much the same, even in areas that were far from the visible edge. This surprising finding was the first strong proof of dark matter, the invisible mass that the outer gas must have in order to keep it in orbit. Over the decades, improvements in radio technology sharpened the picture. Interferometers, arrays of multiple radio dishes working together, provided high-resolution maps of hydrogen across the galactic plane. Observatories such as Arecibo in Puerto Rico, the Parkes Telescope in Australia, and later the Very Large Array in New Mexico filled in the details. They revealed complex structures, long filaments, expanding shells from ancient supernovas, and immense clouds being pulled apart by gravitational tides. The hydrogen wasn't smoothly distributed. It was shaped by star formation, radiation pressure, and galactic rotation. 21-centimeter studies also uncovered the warp of the Milky Way's outer disk. By tracing hydrogen far from the galactic center, astronomers found that the disk isn't flat, but bends upward on one side and downward on the other. This distortion likely results from gravitational interactions with the Magellanic Clouds, or from uneven forces in the surrounding dark matter halo. The discovery showed that our galaxy is not a rigid wheel, but a flexible, living structure, constantly tugged by its environment. Infrared mapping through galactic dust. Stargazers thought for hundreds of years that the dark spots cutting through the Milky Way's bright band were empty spaces. They thought these holes, which they called rifts or lanes, marked the edges between star clouds. The truth was that they weren't empty at all. they were full of tiny dust particles that blocked light. These clouds, which are full of carbon and silicates, block our view of the sky like a screen. 70 of the 1,000 stars that shine in the Milky Way are covered by this dust. To make a map of the galaxy's real size, scientists had to be able to see through it. Infrared astronomy provided the key. Unlike visible light, infrared wavelengths can pass through dust much more easily. The same principle applies on Earth. Infrared cameras can see through smoke or fog because longer wavelengths scatter less. In space, that difference is critical. Where optical telescopes see opaque shadows, infrared telescopes can detect the glow of distant stars and warm gas beyond the veil. This simple property revolutionized how we observe the Milky Way. The first major step came in the late 20th century with NASA's Cosmic Background Explorer, COBE, launched in 1989. Although its main goal was to study the cosmic microwave background, COBE carried an infrared instrument called the Diffuse Infrared Background Experiment, DIRB. DIRB produced the first all-sky infrared maps of the Milky Way, revealing details completely invisible to optical observatories. Instead of dark lanes, COBE showed a glowing network of stars and dust lanes forming the true backbone of our galactic disk. The next leap came with the 2-micron all-sky survey, 2MASS, in the late 1990s. Using twin telescopes in Arizona and Chile, 2MASS scanned the entire sky in near-infrared wavelengths around 2 microns. The survey catalogued nearly 500 million stars and became the foundation for modern galactic structure studies. For the first time, astronomers could trace the Milky Way's central bulge and inner bar with clarity. They discovered that the bar stretches about 27,000 light-years and twists slightly relative to the galactic plane. 2MASS also confirmed that the disk flares outward near its edges and that the density of stars declines gradually rather than abruptly. The shape of the galaxy was revealed by infrared observations, which also mapped more stars. Infrared surveys showed smooth slopes that went deep into the plane, while optical surveys showed spots of uneven light. Scientists made a cross-section of the Milky Way by measuring the number of stars in different directions. The Sun is slightly above the midplane, in a spur between two big arms called Sagittarius and Perseus. This new knowledge improved older radio maps and helped close the gap between where stars and hydrogen are found. Then came the Spitzer Space Telescope, launched in 2003. Operating at mid-infrared wavelengths, Spitzer was powerful enough to pierce even the densest dust near the galactic center. Its high-resolution images revealed intricate filaments of gas, glowing star-forming regions, and dense clusters buried in the heart of the Milky Way. Spitzer's data confirmed the presence of a long, thin central bar and showed that it connects directly to the spiral arms, evidence that the bar drives much of the galaxy's internal rotation and star formation. Spitzer also extended the known stellar disk farther outward. By detecting faint red giants and cool dwarfs beyond optical limits, astronomers found that the galaxy's visible stellar population reaches about 120,000 light-years across. Combined with radio data showing hydrogen even farther out, these infrared findings demonstrated that the Milky Way's luminous component alone is significantly larger than once thought. The surprise discovery of the warp in the galaxy disk by infrared telescopes was another. The Milky Way's surface looks flat from our point of view, but infrared pictures show that its edges curve up on one side and down the other. This warp is most likely caused by gravitational interactions with nearby galaxies like the Magellanic Clouds, or by dark matter being spread out unevenly in the halo. Without infrared light, this feature would have been hidden by the thick dust near the edge of the galaxy. Beyond mapping stars, infrared observations trace the glow of warm dust itself, an essential clue to star formation. Dust absorbs ultraviolet and visible light from young stars, heats up, and re-emits that energy in the infrared. By measuring this glow, scientists can pinpoint regions where new stars are forming, even when those regions are completely hidden in visible light. Spitzer and its European counterpart, the Herschel Space Observatory, mapped thousands of these stellar nurseries across the galactic plane, many located in the spiral arms and at the edge of the disk. These data revealed that star formation continues far beyond what optical images suggested, pushing the galaxy's active zone outward by tens of thousands of light years. The true shape of the Milky Way disk. Astronomy books for most of the 20th century showed the Milky Way as a neat, flat spiral, a beautiful circle with arms that curve around a bright center. It was a comfortable picture that was simple to teach and easy to picture. But the real Milky Way, which has been seen through decades of mapping with many wavelengths, is not at all easy. Its disk is bent, curved, off-center, and always moving. Our galaxy is not a neat account of the universe. Instead, it looks like a spinning piece of cloth being pulled by hands that can't be seen. The first hints that the Milky Way's disk was not flat came from radio observations in the 1950s. When astronomers mapped hydrogen across the galactic plane using the 21-centimeter line, they noticed that gas in the outer regions appeared displaced above and below the midplane. The pattern was consistent across multiple longitudes, suggesting a genuine physical warp rather than an error in measurement. But at the time, it was unclear whether the stars followed the same distortion or if the effect was limited to the diffuse gas. Later, infrared and optical studies confirmed that the stellar disk is also warped. Stars at the galaxy's outer rim rise thousands of light years above the midplane on one side and dip just as far below it on the other. The warp starts to become noticeable around 12 kiloparsecs from the galactic center, roughly 40,000 light years, and becomes more pronounced farther out. In total, the vertical displacement reaches as much as 10,000 light years between the two extremes. To visualize it, imagine a vinyl record left too long in the sun. It still spins, but its edges ripple as it turns. The causes of this distortion are complex. One explanation points to gravitational interaction with the Milky Way's nearest companions, the large and small Magellanic Clouds. These dwarf galaxies, orbiting roughly 200,000 light-years away, are massive enough to tug on the Milky Way's outer gas and stars during their orbits. Computer simulations show that repeated encounters over billions of years could easily twist the disk into its current shape. Another contributing factor may be the uneven distribution of dark matter in the galaxy's halo. If the halo is not perfectly spherical, but slightly elongated, its gravitational pull would apply uneven torque to the disk, bending it into a persistent warp. The Milky Way's disk is not only warped, it's also flared. This means that the further you move from the center, the thicker the disk becomes. Near the galactic core, stars are packed into a relatively thin layer about 1,000 light-years thick. But at a radius of 60,000 light-years, that thickness increases to more than 3,000. The outer disk resembles the rim of a spinning plate curling upward. This flaring likely results from the same forces that cause the warp: external gravitational perturbations and the internal dynamics of the rotating disk. Observations from the European Space Agency's Gaia spacecraft have refined this picture with unprecedented precision. By tracking the motions of over 1 billion stars, Gaia has revealed that the warp is not static. It moves like a wave, slowly precessing around the galaxy's center. The entire warped pattern appears to complete a full rotation roughly every 400 to 500 million years, a motion driven by the combined gravitational influence of the galactic bar and the surrounding dark matter halo. This means the Milky Way's shape is not frozen in time, but continuously shifting, oscillating like a flag rippling in a faint wind. From Earth, the warp changes how we see the Milky Way. The bright band we see in the night sky isn't exactly symmetrical because our solar system is about 26,000 light-years from the center of the galaxy and just above the middle plane. The Milky Way seems to tilt up near Sagittarius and down near Cygnus in the northern hemisphere. This is because the disk really does bend in 3 dimensions. If we could see the galaxy from very high up, it would be amazing how distorted it is. One side of the outer rim would be raised high, and the other side would be falling low, like a spinning saucer that got caught in the middle of a bend. Flaring and warping aren't the only irregularities. The Milky Way's disk is also lopsided. Radio surveys have shown that one half of the galaxy, particularly the side facing the Magellanic Clouds, contains more gas and extends farther than the opposite side. This imbalance may stem from past accretion of intergalactic material or from the gravitational weight created by orbiting companions. Either way, the result is an asymmetric disk that continues to evolve. Figuring out the Milky Way's real shape isn't just a matter of math, it's also important for understanding its past. Over the course of billions of years, the warp and flare show how the forces in our galaxy have changed over time. Each wave and twist tells a story of interactions with smaller galaxies, gas coming in, and dark matter's gravitational pull. Astronomers can figure out how the Milky Way interacts with other galaxies and even get a rough idea of the shape of the unseen ring that surrounds it by modeling these features. Recent data suggest that the warp's motion could also affect star formation. As the outer disk bends, it compresses gas clouds unevenly, creating localized regions of higher density. These pockets can trigger bursts of new star formation along the warp's crest and troughs. The Milky Way, therefore, isn't just warped, it's alive with motion and renewal. The Milky Way's central bar structure. At the center of the Milky Way is a thick, long bar made of billions of stars that you can't see with the human eye, but is very important to how the galaxy behaves. This structure, which is known as the galaxy bar, is about 27,000 light-years long and looks like a spinning beam of light across the inner region. It's not a rare thing. More than 2/3 of spiral galaxies in the universe have bars like this. Astronomers didn't know ours had one for decades, though. It was hidden by dust, distance, and viewpoint until technology got good enough to see through the galactic haze. The first real clues appeared in the late 20th century, when infrared observations began to reveal patterns invisible in optical light. Data from missions such as COBE and later 2MASS showed that the distribution of stars in the galactic center wasn't spherical, as previously assumed. Instead, the brightness stretched along a narrow diagonal axis relative to our line of sight. This odd shape hinted at something more structured, a bar-shaped concentration of old, metal-rich stars orbiting the galaxy's core. Confirmation came in 2005, when the Spitzer Space Telescope delivered high-resolution infrared maps of the central region. Spitzer's images removed the obscuring veil of dust and revealed the full extent of the bar. It begins just a few thousand light-years from the galactic center and extends on both sides like a pair of luminous arms emerging from the bulge. From our vantage point inside the disk, it appears tilted about 27 degrees to the line connecting the Sun and the galactic center. This subtle tilt explains why one side of the central region appears slightly brighter in infrared surveys. It's simply closer to us. But what exactly is this bar, and why does it exist? In dynamic terms, the bar is a concentration of stars following elongated orbits aligned with a common axis. Instead of moving in perfect circles, these stars oscillate back and forth, creating a continuous stream of motion that forms the bar's shape. The bar rotates as a single unit, completing one full revolution every 100 million years or so. Its rotation speed and gravitational influence make it a dominant driver of galactic evolution. Bars are not static structures, they are engines. The Milky Way's bar channels gas inward from the spiral arms toward the center, fueling bursts of star formation near the core and feeding the supermassive black hole, Sagittarius A star. This flow of material explains the rich population of young stars, molecular clouds, and high-energy activity in the central few thousand light-years. The bar acts like a conveyor belt, moving matter from the outer disk toward the inner regions, sustaining the galaxy's ongoing cycle of creation. The bar also shapes the Milky Way's spiral arms. As it rotates, its gravitational torque compresses gas along specific orbital paths, forming the bases of the spiral arms that extend outward. In essence, the bar is the galaxy's steering wheel, controlling the pattern and symmetry of the entire disk. Computer simulations show that without it, the Milky Way's spiral structure would likely be weaker or even vanish over cosmic timescales. New information from the Gaia mission has helped us understand how the bar moves better. By keeping track of how stars move in the inner galaxy, scientists can make models that show how the bar's gravity field affects everything nearby. The data show that the bar isn't exactly straight. It's a little boxy and thicker in the middle, where older stars are more common. This area rises thousands of light years above and below the galactic plane. It is sometimes called the peanut-shaped bulge. This bar was made when the inner disk became unstable billions of years ago. It buckled under its own weight and rearranged itself into the shape we see today. Spectroscopic studies reveal that stars in the bar are generally older and more metal-rich than those in the outer disk, suggesting that the bar formed early in the Milky Way's history and has since evolved slowly. It likely grew longer and stronger as it transferred angular momentum to the surrounding disk, a process confirmed by computer simulations. Over time, this redistribution of momentum reshapes the entire galactic interior, altering rotation curves and triggering waves of star formation at the bar's ends. The bar has an effect that goes far beyond the center bulge. It has gravity resonance zones that go tens of thousands of light years into the disk and change the paths of stars, even ones close to our solar system. Some of the strange moves seen in nearby star groups might be caused by the bar's faraway gravitational pull. There are small bumps in the Milky Way's spin path that this effect helps explain, but that local mass alone couldn't. Observations also showed that the Milky Way's bar may not be perfectly stable. Data from Gaia and Spitzer indicate that the bar might be slowing down, likely due to interactions with dark matter in the halo. As the bar rotates, it transfers angular momentum to surrounding matter, causing it to lengthen and decelerate over time. This gradual slowdown influences how gas flows into the inner galaxy and could eventually reshape the spiral pattern itself. Reconstructing spiral arms with Gaia data. The bar has an effect that goes far beyond the center bulge. It has gravity resonance zones that go tens of thousands of light years into the disk and change the paths of stars, even ones close to our solar system. Some of the strange moves seen in nearby star groups might be caused by the bar's faraway gravitational pull. There are small bumps in the Milky Way's spin path that this effect helps explain, but that local mass alone couldn't. Launched in 2013, Gaia's goal was deceptively simple: measure the positions, brightness, and motions of more than 1 billion stars. But the precision of those measurements, down to micro-arcseconds, redefined what was possible. Each star's parallax provides its distance, and its proper motion reveals its direction of travel. When combined, these data turn the flat night sky into a volumetric model, allowing astronomers to trace not just where stars are, but how they move through the galaxy. The result is a living map of the Milky Way's structure in motion. Before Gaia, the Milky Way's spiral structure was largely inferred from radio observations of hydrogen gas and molecular clouds. These maps suggested 4 major arms: Perseus, Sagittarius, Scutum Centaurus, and Norma, with our Sun located in a smaller branch called the Orion Arm, or local spur. Yet those radio maps measured gas, not stars, and the arm's exact positions remained uncertain by tens of thousands of light years. Gaia provided the missing link: direct stellar mapping across the entire disk. When Gaia's early data releases were combined with surveys of massive young stars, O and B-type stars that form exclusively within spiral arms, the outlines began to sharpen. Astronomers could finally see the arms' curves as real stellar overdensities rather than abstract models. The results confirmed 2 dominant arms, Perseus and Scutum Centaurus, flanked by several shorter segments and spurs, including the one that hosts our solar system. The pattern is asymmetric and irregular, more like a series of intertwining streams than perfectly drawn coils. Gaia also revealed that spiral arms aren't solid structures, but rather density waves, regions where stars and gas crowd together as they orbit the galaxy. Stars move in and out of these zones, just as cars move through traffic congestion. A spiral arm is not a fixed collection of stars. It's a continuous pattern of compression moving through the disk. Gaia's motion data provided direct evidence of this behavior. Stars on the leading edges of arms slow slightly, while those trailing behind accelerate, matching predictions of the density wave theory first proposed in the 1960s. The accuracy of Gaia's lengths between stars has also made it easier to see the pitch angle of each arm, which is the angle at which it winds away from the center of the galaxy. The Milky Way's arms bend outward at an average angle of about 12 degrees, but this changes from arm to arm. For example, the Scutum Centaurus arm is tighter and closer to the middle, while the Perseus arm goes out to the edges in a less tight way. We live in the Orion arm, which is only a few thousand light-years wide and about 10,000 light-years long. This means that our Sun is close to the inner edge of it. In addition to mapping arm geometry, Gaia uncovered the vertical structure of the disk within and between arms. By measuring how stars oscillate above and below the galactic plane, astronomers discovered waves in the stellar distribution, ripples possibly triggered by past gravitational encounters with satellite galaxies. These ripples may also influence the spacing of the spiral arms, suggesting that the Milky Way's shape is constantly evolving rather than fixed. Gaia also made a crucial discovery. The spiral arms hold stars from different generations. In earlier models, arms were thought to be ruled by young, huge stars. The arms can be seen because of these bright stars. But Gaia's collection shows that many older stars move in the same ways. This means that the arms are not temporary features that form and disappear every few 100 million years. Instead, they are long-lasting structures that are kept in place by gravity resonance and the center bars effect. By cross-referencing Gaia's stellar data with radio and infrared maps, astronomers have also traced the flow of interstellar gas through the arms. Gas tends to pile up along the inner edges of the arms, where it is compressed and triggers star formation. Once newborn stars emerge, they drift slightly outward, illuminating the surrounding dust and creating the bright, glowing regions captured in infrared images. This interplay between gas flow and star birth explains why spiral arms shine so prominently in every wavelength. The combination of Gaia's stellar motions and chemical data, obtained from its onboard spectrograph, has given even more depth to the map. Stars with higher metallicity, heavier elements, tend to cluster nearer the galactic center, while metal-poor stars dominate the outer arms. This gradient reflects billions of years of stellar recycling and helps astronomers trace how the Milky Way grew outward over time. The thickness and flare of the outer disk. If you think of a spiral galaxy, you might picture a thin, flat disk of stars moving slowly around a bright center. Scientists have said for decades that the Milky Way is thin and smooth, like a record from space. But new scans show that the edges of our galaxy are not flat at all. The outer disk doesn't end in a neat point. It flares outward and inward, getting much thicker as it goes deeper into space. The Milky Way doesn't look much like a flat plate. Instead, it looks more like a moving saucer with bent, uneven edges. The first clues came from radio astronomy in the 1960s. When researchers mapped neutral hydrogen gas at 21 centimeters, they noticed that the gas layer far from the galactic center grew thicker with distance. Instead of tapering off, the hydrogen extended thousands of light-years above and below the galactic plane. This effect became even clearer when infrared surveys began measuring the positions of distant stars. Near the center of the Milky Way, the stellar disk is remarkably thin, only about 1,000 light-years thick. But at distances of 60,000 light-years or more, the thickness is more than triples. The flaring of the galactic disk refers precisely to this widening. The farther you move outward from the center, the less tightly gravity holds the gas and stars. In the inner regions, The galaxy's gravitational pull, produced by its dense concentration of stars and dark matter, keeps everything confined to a narrow plane. At the outskirts, where gravity weakens, even small disturbances from passing dwarf galaxies, gas inflows, or the surrounding dark matter halo can push material out of alignment. Over billions of years, these vertical oscillations accumulate, forming a visible flare. Data from the Gaia spacecraft have allowed astronomers to measure this structure in fine detail. By tracking the three-dimensional positions and velocities of hundreds of millions of stars, Gaia has shown that the Milky Way's flare begins around 12 kiloparsecs, about 40,000 light-years, from the galactic center. Beyond that radius, the density of stars decreases, but the vertical spread increases rapidly. At the outermost regions, roughly 60 to 70,000 light-years away, the stellar layer can span several thousand light-years in height. The flare isn't symmetrical. On one side of the galaxy, it extends farther than on the other, consistent with gravitational disturbances from neighboring dwarf galaxies. The large and small Magellanic Clouds, orbiting roughly 200,000 light-years away, are likely culprits. Their combined gravitational pull exerts a steady, uneven force on the Milky Way's outskirts. Numerical simulations show that their passage over billions of years could easily have generated the warp and flare now seen in the outer disk. The flash is especially interesting because it's not just gas. Stars are also working in it. Infrared and near-infrared studies, like 2MASS and WISE, have shown that this upward curve is also shared by older, redder stars. This means that the outer galaxy's whole structure of stars is literally bent and made thicker. The process probably started early in the Milky Way's past when it collided with smaller galaxies and changed its shape. It has been going on ever since. Spectroscopic data provide further insight. By analyzing the chemical composition of stars in the flared regions, astronomers discovered a mix of populations, some metal-rich stars typical of the inner disk, and others more metal-poor, similar to halo stars. This suggests that the flare is not a single continuous population, but a dynamic mixture of materials stirred by past mergers. Some of the outer stars may even be debris from dwarf galaxies torn apart and absorbed by the Milky Way. The flare also connects closely with the thick disk, another layer of the Milky Way that lies between the thin, bright stellar plane and the faint halo above it. The thick disk contains older stars, many with lower metallicity, and extends several thousand light-years on either side of the galactic midplane. In the outer regions, the thick disk and the flare appear to merge, forming a smooth transition from structured disk to diffuse halo. This blending challenges astronomers to define where the disk truly ends and where the halo begins. When it comes to dynamics, the flare has clear effects that can be measured. As the stars in it circle the center of the galaxy, their paths are slightly tilted, going above and below the plane of the galaxy. This motion makes small vertical waves in the spread of stars. Gaia's precise velocity data reveal that these oscillations are not random. They form coherent patterns, likely triggered by gravitational shocks from encounters with satellite galaxies or from passing through the dense midplane of the disk. The flare's presence also affects how we interpret the galaxy's mass distribution. Because the outer regions rise and thicken, estimates of total mass based solely on a flat disk model would be inaccurate. Accounting for the flare adds substantial volume to the galactic structure, increasing the estimated number of stars and amount of gas contained within the Milky Way. Infrared imaging and simulations show that the flare may continue to evolve. As the galaxy rotates and interacts with its neighbors, the outer disk bends and flexes like a living membrane. Gas falling in from intergalactic space can pile up along the flared edges, replenishing the material that fuels new star formation. In this way, the flare isn't just a relic of past events. It's an active boundary where the Milky Way exchanges matter with its environment, the stellar halo and its outer limit. The stellar halo is a huge, faint, and very old structure that goes around the bright curving disk of the Milky Way. It is made up of a cloud of nearly spherical stars that runs hundreds of thousands of light years in every direction. The galactic disk is the Milky Way's body, and the halo is its ghostly atmosphere. It is made up of so few stars that you might only be able to see one at a time if you were in a spaceship going through it. Still, this fuzzy ring holds important secrets about the galaxy's real size and its long, violent past. The first evidence of the halo appeared early in the 20th century, when astronomers noticed that certain faint stars didn't move with the same orderly rotation as those in the galactic plane. These stars had highly elliptical orbits that took them far above and below the disk. In 1918, Harlow Shapley used the positions of globular clusters, dense spherical groups of hundreds of thousands of old stars, to infer that they formed a roughly spherical distribution around the Milky Way. This was the first hint that our galaxy was surrounded by a much larger three-dimensional structure invisible in ordinary starlight. Today, the stellar halo is recognized as a sprawling component extending at least 300,000 light-years from the galactic center and possibly farther. It contains some of the oldest stars in existence, low-mass, metal-poor survivors formed when the universe was still young. These stars are cosmic fossils, preserving the chemical signatures of the Milky Way's earliest epochs. By studying them, astronomers can reconstruct how our galaxy assembled from smaller fragments billions of years ago. Unlike the thin, rotating disk, the stellar halo is kinematically chaotic. Its stars move in random directions rather than orbiting neatly in a plane. This irregularity points to its origin. The halo is largely built from the debris of galactic mergers, smaller galaxies that were captured and torn apart by the Milky Way's gravity. Over time, their stars spread out along long, looping trajectories, forming a nearly spherical cloud. Each generation of mergers added more stars to the halo, layering the Milky Way like geological strata in rock. The Gaia spacecraft has been crucial in mapping the positions and motions of halo stars. By plotting their velocities, astronomers have identified distinct groups that once belonged to separate galaxies. One of the most prominent of these is the Gaia Sausage-Enceladus merger, a massive collision that occurred about 10 billion years ago. The remnants of that ancient galaxy now form a large portion of the inner halo, and their stars can still be identified by their unique, elongated orbits and low metal content. As Gaia's data extends outward, it reveals streams of stars arcing through the halo, tidal remnants of even more recent mergers. Among the most striking is the Sagittarius Stream, a colossal ribbon of stars torn from the Sagittarius dwarf galaxy as it spirals into the Milky Way. This stream wraps almost completely around the galaxy, tracing the halo's shape like a luminous scaffold. Observations of these streams allow astronomers to map the halo's outermost boundaries and measure the gravitational pull of the Milky Way far beyond its visible edge. The halo doesn't just contain stars. It's also home to many of the galaxy's globular clusters, which orbit in extended paths reaching far into intergalactic space. Some of these clusters lie more than 150,000 light-years from the galactic center, so distant that they are nearly halfway to the Andromeda galaxy's own halo. These remote clusters mark the visible limit of the Milky Way's stellar domain, though faint stars and streams likely continue even farther. The density of the halo decreases smoothly with distance, fading by orders of magnitude as one moves outward. There's no hard boundary, just a gradual transition where the gravitational influence of the Milky Way merges into that of its neighboring galaxies. The outer halo is so diffuse that its stars are separated by enormous distances, sometimes dozens of light-years apart. In those lonely regions, the galaxy's light is faint and its motion slow, but its reach remains measurable. Chemical studies have helped us learn more about the nature of the halo. Astronomers can use spectroscopy to find out how solid a star is, which means how many heavy elements it has. Most halo stars have metallicities that are hundreds of times smaller than those in the Sun. This means that they formed before the Milky Way made a lot of heavy elements through stellar fusion. The metallicity tends to drop as you move farther away from the center of the galaxy. This suggests that the outer region is mostly made up of stars that were caught from younger, simpler galaxies. To its ancient stars, the halo plays an essential role in defining the Milky Way's total mass. By observing the motions of globular clusters and distant halo stars, scientists can infer how much gravity the galaxy exerts at great distances. The results consistently indicate that visible matter, stars, gas, and dust accounts for only a fraction of the mass required to explain those motions. The rest must come from dark matter, which dominates the halo's outer regions and extends far beyond the reach of normal starlight. Mapping the dark matter halo. There would be a huge circular web of dark matter left over from the Milky Way if all of its stars, planets, and gas clouds were taken away. It's not shiny, it doesn't take in light, and you can't see it directly. Still, it holds more than 90% of the galaxy's mass and tells us how big it really is. Dark matter ring is like the Milky Way's secret skeleton. It's what holds everything together, but you can't see it. The evidence for its existence dates back to the mid-20th century. When astronomers measured how fast stars orbit around the galactic center, they noticed something strange. According to Newtonian physics, objects farther from the center of mass should orbit more slowly, just as the outer planets in our solar system move slower than the inner ones. But when scientists plotted the Milky Way's rotation curve, orbital speed versus distance from the center, they found that beyond a certain point, the speed didn't drop off. It stayed nearly constant, even far beyond the visible edge of the galaxy. This observation made no sense if only visible matter existed. The stars and gas we can see simply don't provide enough gravitational pull to keep the outer stars moving that fast. Without additional mass, those stars should have drifted into space long ago. The only explanation was that the Milky Way, like other galaxies, must be surrounded by a massive halo of unseen matter. This invisible halo provides the extra gravity needed to hold the galaxy together. Estimating the shape and size of the dark matter halo is a challenge unlike any other. Because it cannot be observed directly, astronomers rely on the motions of objects within and around the galaxy to infer its properties. They study the orbits of globular clusters, satellite galaxies, and distant halo stars to measure the gravitational field at great distances. The faster these objects move, the more mass must be present. Early models suggested that the Milky Way's dark matter halo extends at least 10 times farther than the visible stellar disk, up to nearly 2 million light-years in diameter. Its total mass is estimated to be about 1 to 2 trillion times that of the Sun. Within this vast sphere, dark matter forms a smooth, diffuse distribution that gradually decreases in density with distance. Unlike the luminous parts of the galaxy, which rotate as a disk, the halo is roughly spherical, enveloping everything in a gravitational cocoon. Modern simulations using supercomputers have helped refine this picture. In cosmological models such as Illustris and Eagle, galaxies like the Milky Way form when dark matter clumps under gravity, creating halos that attract gas. That gas cools, collapses, and eventually forms stars and disks. The visible galaxy, then, is just the central region of a much larger dark matter structure. In these simulations, the halo's shape isn't perfectly round. It's slightly elongated, often resembling a squashed sphere or triaxial ellipsoid. Interactions with nearby galaxies like Andromeda and the Magellanic Clouds can also distort it, stretching the halo into irregular shapes over billions of years. The motion of the Sagittarius Stream, a long ribbon of stars stripped from the Sagittarius dwarf galaxy, has been particularly useful in tracing the Milky Way's halo. By modeling how this stream bends and twists under gravity, scientists can map the underlying mass distribution. The stream's orbit indicates that the halo extends far beyond the outermost stars, and that it may be slightly flattened towards the galactic plane. Similar analyses using the orbits of other satellite galaxies, such as the Magellanic Clouds and Draco, help constrain the halo's density profile. Astronomers also use the escape velocity method to estimate the halo's total mass. This involves measuring how fast stars and gas must move to break free from the Milky Way's gravity. Recent data from Gaia show that even the fastest known stars, so-called hypervelocity stars, are still bound to the galaxy, implying an enormous gravitational reach. The results are consistent with a halo mass of roughly 1.2 trillion solar masses, encompassing a region almost halfway to the Andromeda galaxy. Dark matter doesn't interact with light, but it leaves indirect traces. One is gravitational lensing, the bending of light from distant galaxies as it passes through the halo. Though subtle, this effect can be measured statistically across large regions of sky. Weak lensing surveys using instruments like the Hubble Space Telescope and the Dark Energy Survey have detected these distortions, confirming that the Milky Way's halo extends far beyond the range of its stars. Moving of the galaxy corona or ring of hot gas that surrounds the Milky Way is another sign. Through X-ray observations, we can see that the galaxy's gravity keeps this gas in place over hundreds of thousands of light years. The amount of dark matter needed to hold it is the same as what we can figure out from spin curves and satellite movements. This makes the case for a large, extended halo even stronger. The hot gas halo, galactic corona. There is a huge ocean of unseen heat around the Milky Way's bright disk and faint star halo. This is the galactic corona, which is a sphere of ionized gas. This huge sphere goes out into space so far that it might touch the halo of the Andromeda galaxy, which is close by. It can't be seen with regular light, but it glows slightly in X-rays, showing that our galaxy is surrounded by a huge million-degree atmosphere. There was discussion about its presence for decades. It is now known to be one of the biggest and most important parts of the Milky Way. Hints of this hot gas halo first appeared in the 1960s, when X-ray detectors aboard early space probes began registering faint, diffuse radiation coming from all directions. At first, astronomers thought these signals might come from distant quasars or the cosmic background. But further analysis revealed something different. A significant portion of the soft X-rays originated much closer, from gas bound to our own galaxy. The Milky Way, it turned out, wasn't surrounded by empty space. It was enveloped by a superheated cloud. This gas is extraordinarily thin by earthly standards, with densities of only a few particles per cubic centimeter, far emptier than any vacuum humans can create. Yet it's spread across such a vast volume that its total mass may rival or exceed all the stars in the Milky Way combined. The corona's temperature ranges from 1 to 3 million Kelvin, hot enough to strip atoms of their electrons and produce a continuous glow in ultraviolet and X-ray wavelengths. Modern X-ray observatories like Chandra, XMM Newton, and Suzaku have mapped the corona in unprecedented detail. They detect emission from highly ionized elements, such as oxygen, neon, and iron, which act as tracers for the hot gas. These observations show that the corona extends at least 200,000 to 300,000 light-years from the galactic center, possibly more. Some models suggest it stretches nearly to the halfway point between the Milky Way and Andromeda. If so, the two galaxies' coronas may already be mingling, a quiet prelude to their eventual merger billions of years from now. But the corona isn't uniform. It appears denser and hotter near the galactic center, thinning gradually toward the outskirts. Embedded within it are cooler, denser clouds and streams of gas, possibly remnants of small galaxies that were torn apart and mixed into the halo. Observations of quasar light passing through these regions have revealed absorption lines from different ionized species, confirming the corona's layered structure, hot inner gas surrounded by cooler filamentary outer shells. The origin of this massive halo traces back to the Milky Way's formation. As the galaxy grew through mergers and accretion, infalling gas was heated to extreme temperatures by the energy of gravitational collapse. Some of it cooled to form stars and the visible disk, but a large fraction remained hot and diffuse, trapped in the galaxy's gravitational field. Over billions of years, supernova explosions and stellar winds have continued to inject energy and material into this halo, replenishing and maintaining its high temperature. The corona also plays a critical role in the galactic ecosystem. It acts as a reservoir of raw material for future star formation. Cooler clouds falling from the outer halo can condense and rain down onto the galactic disk, feeding new generations of stars. At the same time, energetic events such as supernovae and black hole activity push gas outward, enriching the halo with heavier elements. This constant cycle of inflow and outflow links the disk to its surroundings in a delicate balance. The two huge Fermi bubbles, which are bands of high-energy radiation 25,000 light-years above and below the galactic plane, are one of the most captivating discoveries found in the corona. NASA's Fermi Gamma-ray Space Telescope found these bubbles in 2010. They are full of hot plasma and powerful particles that may have been thrown out by the supermassive black hole Sagittarius A star during a period of activity millions of years ago. The bubbles show that the corona is not still, but is moving and turbulence-filled because of strong events at the center of the galaxy. It's hard to say how much mass the corona has, but new research that combines X-ray data with ultraviolet absorption observations from the Hubble Space Telescope suggests that it might hold up to half of the Milky Way's baryonic matter, which is made up of protons and neutrons. Astronomers have known for a long time that galaxies didn't seem to have as much visible matter as cosmic models suggested. Since the galactic corona was found, that gap has shrunk. A lot of the missing matter is still there. It's just too hot and spread out to be easily found. The corona's existence also affects how we define the true size of the Milky Way. Traditionally, astronomers measured the galaxy's diameter by the distribution of its stars or hydrogen gas, stopping where the density drops too low to detect. But if the corona extends hundreds of thousands of light-years farther, then the Milky Way's effective radius is far larger than once thought. When this extended hot halo is included, the galaxy's diameter may approach 1.5 to 2 million light-years, nearly matching the reach of its dark matter halo. Galactic magnetic fields. Magnetic fields run through the Milky Way like invisible currents, affecting everything from the birth of stars to cosmic radiation. Even though they can't be seen directly, their marks can be seen everywhere, in the reflected glow of stars, in the direction of radio waves, and in the tracks that high-energy cosmic rays take as they move through the galaxy. Astronomers thought for many years that magnetism had only a small part in the formation of galaxies. Now we have proof that it is fundamental, an unseen framework that affects gas, dust, and even the movement of charged particles over hundreds of thousands of light-years. The first clues of magnetic structure came in the 1940s, when astronomers noticed that starlight was partially polarized as it passed through interstellar space. Polarization occurs when light waves align along a common orientation, something that happens when light scatters off dust grains oriented by a magnetic field. This simple observation meant that space between the stars wasn't random. It contained an ordered magnetic influence. Later, radio astronomers detected another hallmark: synchrotron radiation, radio waves emitted by electrons spiraling through magnetic fields at nearly the speed of light. These discoveries marked the birth of galactic magnetism as a real field of study. The Milky Way's magnetic field is weak by human standards, averaging only a few microgauss, roughly a millionth the strength of a typical refrigerator magnet. Yet its reach makes it powerful. Over distances of thousands of light-years, even such faint fields can direct the motion of ionized gas, channel cosmic rays, and help shape the overall structure of the interstellar medium. The field runs roughly parallel to the galactic plane, following the spiral arms in large-scale loops. This alignment suggests it is tightly coupled with the galaxy's rotation and the flow of gas through its arms. Scientists rely on the Faraday rotation effect, in which the polarization of radio waves twists as they pass through a magnetized plasma. By measuring the amount of rotation across different regions of the sky, astronomers can infer both the strength and direction of the field. Data from surveys such as the Canadian Galactic Plane Survey and the Galfax project reveal that the Milky Way's magnetic field follows a coherent spiral pattern, reversing direction several times between arms. These reversals are signatures of a large-scale dynamo mechanism, a process by which the motion of conducting gas generates and maintains magnetic fields, similar to how Earth's core produces its own magnetism. The Milky Way's dynamo operates on galactic scales. As the galaxy rotates, differential motion between inner and outer regions twists and stretches magnetic field lines. Turbulence in the ionized gas amplifies them, converting rotational energy into magnetic energy. Over billions of years, this self-sustaining cycle keeps the galactic field alive. Numerical simulations confirm that such dynamos can reproduce the field strengths and patterns observed in the Milky Way and other spiral galaxies. Magnetic fields influence almost every process in the interstellar medium. They help regulate star formation by supporting clouds of gas against gravitational collapse. When molecular clouds begin to condense, magnetic pressure resists the inward pull of gravity, slowing the rate at which stars form. Only when the magnetic field weakens or matter becomes sufficiently dense does collapse proceed, allowing a star to ignite. In this way, magnetism acts as a moderator, preventing galaxies from turning all their gas into stars too quickly. On larger scales, magnetic fields shape the filamentary structure of gas and dust throughout the Milky Way. Infrared images from the Planck Space Observatory show long strands of dust aligned with magnetic field lines, stretching across thousands of light-years. These filaments trace the invisible currents threading the galactic disk, connecting regions of star formation and guiding material into the spiral arms. The field also governs the behavior of cosmic rays, high-energy particles produced by supernova explosions and black hole activity. Without magnetic fields, these particles would stream freely into space. Instead, they are trapped, spiraling along field lines and scattering through the galaxy for millions of years. This confinement creates a cosmic ray pressure that influences gas dynamics and contributes to the galactic wind, a slow outflow of material from the disk into the halo. Beyond the plane, magnetic fields extend into the Milky Way's corona and even into intergalactic space. Observations of polarized radio emission show vertical magnetic structures rising tens of thousands of light-years above the disk, likely formed by outflows from supernovae or activity near the galactic center. These vertical filaments may channel hot gas and cosmic rays outward, linking the disk to the halo in a vast dynamic circuit. The Fermi bubbles above and below the core. Astronomers using NASA's Fermi Gamma-Ray Space Telescope to study the night sky made one of the most amazing finds in the field of modern galactic astronomy in 2010. They saw two huge, symmetrical bands of high-energy radiation rising from the center of the Milky Way. The Fermi bubbles are these bright structures that stretch about 25,000 light-years above and below the galactic plane. They are much bigger than our solar system, and are even bigger than the Milky Way's visible disk thickness. They give off tiny glows in gamma rays, X-rays, and microwaves, showing that our galaxy's history was violent and released huge amounts of energy. For years, astronomers had suspected that something unusual lurked near the galactic center. Observations in radio and X-ray wavelengths hinted at strange arcs and ridges, but no one imagined structures of this scale. When Fermi's detectors revealed them in full, the symmetry was unmistakable. Two vast bubbles, mirror images of each other, rising like plumes from the Milky Way's central region. Their edges are sharply defined, indicating that whatever created them acted both rapidly and powerfully. Each bubble contains tens of millions of solar masses worth of hot gas and relativistic particles moving at thousands of kilometers per second. The total energy stored in these structures is estimated at 1055 eargs, roughly equivalent to the combined energy of 100,000 supernovae. To put that in perspective, that's about the amount of energy our Sun would emit over its entire 10 billion year lifetime, released in a single galactic scale event. The question immediately arose: what could possibly cause such a phenomenon? Two major theories emerged, both rooted in the extreme activity near the Milky Way's core. The first proposes that the supermassive black hole, Sagittarius A*, once erupted in a powerful accretion event, Normally, our black hole is quiet, feeding only sporadically on infalling gas, but like volcanoes, it may experience rare outbursts when enough material accumulates. During such a flare-up, the infalling gas would heat to millions of degrees and eject jets of plasma perpendicular to the galactic plane, inflating the massive bubbles we now see. The second hypothesis attributes the bubbles to a burst of star formation, a starburst event that triggered thousands of supernovae near the galactic center. The combined winds and shock waves from these explosions could have blasted hot gas into the halo, carving the twin lobes in the process. Either explanation involves enormous power, but both fit the observations: high temperatures, metal-enriched gas, and a structured boundary where hot plasma meets the cooler galactic halo. The age of the Fermi bubbles remains an open question. Most studies suggest they were formed between 3 and 6 million years ago, a blink of an eye in cosmic terms. That timing intriguingly coincides with signs that Sagittarius A** was far more active in the recent past. Infrared observations show long, narrow filaments extending from the galactic center, possibly remnants of past jets. Even today, gas clouds near the core exhibit shock patterns consistent with outflows from a powerful central source. In 2020, NASA's Rosetta telescope added a new piece to the puzzle. It detected even larger, fainter X-ray lobes extending beyond the Fermi bubbles, dubbed the Rosetta bubbles. These structures stretch nearly 45,000 light-years in each direction, almost twice as large as the original gamma-ray bubbles. Together, they form a multi-layered system of galactic outflows, revealing that our galaxy's central black hole has likely erupted multiple times throughout its history. Sagittarius A*, the supermassive black hole at the core. There is something so big and dense in the middle of the Milky Way that not even light can get away from it. It is hidden behind thick clouds of dust and gas. This is Sagittarius A*, which is called A*. It is the huge black hole that holds our galaxy together. It has about 4 million times the mass of the Sun squished into an area no bigger than Mercury's orbit. Even though it can't be seen, its gravitational pull affects everything around it. Stars, gas clouds, and even the spiral arms of the galaxy move in response to its presence. For decades, astronomers suspected that something extraordinary lurked at the galactic center. In the 1950s, radio telescopes detected a strong source of emissions coming from the constellation Sagittarius, near the direction of the Milky Way's densest region. This mysterious object, later named Sagittarius A, emitted radio waves that didn't match any known type of star. As instruments improved, scientists discovered that the emission came from an incredibly compact region. The conclusion was unavoidable. Only a black hole could explain the data. Definitive proof arrived in the late 20th and early 21st centuries thanks to a remarkable series of observations led by astronomers Andrea Ghez and Reinhard Genzel, who would later share the 2020 Nobel Prize in Physics. Using infrared telescopes at the Keck Observatory in Hawaii and the Very Large Telescope in Chile, they tracked the orbits of stars near the galactic center for more than 2 decades. These stars, known as the S-stars, move at blistering speeds, some exceeding 7,000 kilometers per second, completing full orbits in just a few years. Their paths trace perfect ellipses around an invisible point in space. By applying Kepler's laws of motion, researchers calculated that this unseen object must have a mass equivalent to 4 million suns, yet be smaller than our solar system. No cluster of ordinary stars or exotic particles could fit those parameters. The only possible explanation: a supermassive black hole. Sagittarius A* doesn't behave like the luminous quasars seen in distant galaxies. It's relatively quiet, feeding only occasionally on infalling gas. Most of the time, it emits a faint glow across the radio, infrared, and X-ray spectrum, a sign that only a small trickle of matter is being consumed. But during rare flares, its brightness can spike by a factor of hundreds in just a few minutes. These bursts likely occur when clumps of gas spiral inward and heat up to millions of degrees before crossing the event horizon, the point of no return. In 2022, astronomers achieved one of the most extraordinary milestones in astronomy, the first ever image of Sagittarius A star's shadow, captured by the Event Horizon Telescope, EHT. This global network of radio observatories effectively turned Earth into a planet-sized telescope through a technique called very long baseline interferometry. The resulting image revealed a glowing ring of hot plasma orbiting a dark center, the black hole's shadow. It confirmed Einstein's predictions from general relativity with astonishing precision. The light we see in the image has been warped by gravity, bent around the event horizon before escaping toward Earth. The region around Sagittarius A star is a place of extreme physics. Magnetic fields twist and snap, launching bursts of radiation, and sometimes even faint jets of particles that shoot outward from the accretion disk. Time itself slows down under its immense gravity. If you could orbit close to the event horizon, you'd experience gravitational time dilation. Seconds for you would pass as years for someone far away. Despite its terrifying reputation, Sagittarius A star is a stabilizing presence. Its gravity helps organize the motion of millions of stars in the central bulge and influences the overall structure of the galaxy. Without this massive anchor, the inner regions of the Milky Way would be far more chaotic. Astronomers continue to study how Sagittarius A star interacts with its surroundings. Recent observations have shown clumps of gas and even entire stars venturing dangerously close to the black hole. In 2014, a cloud known as G2 approached within just 20 billion kilometers of the event horizon. Many expected it to be torn apart and devoured, but instead, G2 survived the encounter, though visibly stretched and distorted. Its resilience raised new questions about the black hole's feeding habits and the density of material near its core. The Andromeda collision, a future galactic merger. The Andromeda galaxy, M31, is a faint, long blur in the night sky. It is about 2.5 million light-years from Earth, across the empty space between galaxies. It looks small and safe at first glance, just another spiral in a sea of billions. The real Andromeda, on the other hand, is a 1 trillion solar mass monster coming at us at more than 250,000 miles per hour. It's the nearest big galaxy to the Milky Way. And one day it will crash into us in a huge explosion that will change the sky and create a whole new galaxy. The impending impact between the Milky Way and Andromeda isn't a matter of speculation. It's a physical certainty. Using the Hubble Space Telescope, astronomers have precisely measured Andromeda's motion through space. Its blue shifted light reveals that it is moving toward us rather than away, defying the general expansion of the universe. When combined with Gaia's measurements of stellar motion within our own galaxy, the data leave no doubt. Our two galaxies are on a direct collision course that will culminate about 4.5 billion years from now. At first glance, the term collision sounds catastrophic, but on a galactic scale, it's far more graceful than violent. Although each galaxy contains hundreds of billions of stars, the space between them is vast. So vast that the probability of any two stars actually striking one another is almost zero. When Andromeda meets the Milky Way, their stars will mostly pass between one another, guided by gravity's invisible hand. The true collision happens between their gravitational fields, gas clouds, and dark matter halos. As the two galaxies approach, their outer dark matter halos, each spanning nearly 2 million light-years, will begin to merge long before the visible disks touch. In a sense, the interaction has already begun. The overlapping halos exert tidal forces that subtly distort both galaxies' outer regions. Streams of stars and gas will stretch out into space, forming long tidal tails and bridges as the galaxies exchange material. When the galactic disks finally interpenetrate, roughly 4 billion years from now, the night sky from Earth, or whatever remains of it, will transform beyond recognition. Andromeda will swell from a faint smudge into a vast, glowing spiral, eventually dominating the entire sky. Over several 100 million years, the two galaxies will begin to intertwine. Gravitational interactions will compress clouds of gas and dust, triggering spectacular bursts of star formation. New clusters of brilliant blue stars will ignite along the tidal bridges, briefly lighting up the darkness between galaxies. The central regions will fare differently. As the supermassive black holes, Sagittarius A star in the Milky Way and Andromeda's central black hole, draw closer, they will spiral toward each other, releasing tremendous amounts of energy in gravitational waves. Eventually, they will merge into a single, even larger black hole, containing the combined mass of about 10 million suns. That merger will produce a gravitational wave signal strong enough to ripple across the entire local group of galaxies. Over the next billion years, the structure of both galaxies will change completely. The elegant spiral arms of the Milky Way and Andromeda will dissolve, replaced by a vast elliptical remnant, a featureless, football-shaped cloud of stars. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. Its stellar population will settle into new orbits around a common center, the merged black hole shining faintly at its core. Computer simulations, such as those created by NASA's Hubble and Chandra teams, give us a window into this distant future. They show that after the first close pass, the galaxies will swing apart slightly before gravity pulls them back together. Several passes and mergers will follow before the system stabilizes. Each encounter will strip away more angular momentum, heating and mixing the stars into a smooth, featureless distribution. The entire process, from first contact to full merger, will take roughly 5 to 6 billion years. The collision will also rearrange our solar system's position within the new galactic structure. Depending on the precise geometry of the merger, the Sun may be flung into a wide, eccentric orbit far from the core, or possibly ejected into intergalactic space entirely. Even if it remains bound to the merged galaxy, the night sky seen from any surviving planet will never be the same. Instead of a thin, hazy band of the Milky Way, future observers will gaze upon a dense, glowing field of stars stretching in all directions, a sky ablaze with cosmic light. Meanwhile, the merged galaxy will continue forming stars for billions of years, fueled by the collision-driven compression of gas. Over time, however, that supply will dwindle. The massive bursts of star formation will exhaust much of the available gas, leaving behind a population of aging red and yellow stars. Eventually, Milkomeda will fade into a quieter, redder state, resembling the giant elliptical galaxies that dominate galaxy clusters today. Galactic cannibalism, how the Milky Way grows by eating smaller galaxies. Like living things, galaxies grow by both absorbing other galaxies and growing themselves. The Milky Way is no different. Galactic cannibalism, the act of pulling in and eating smaller neighbor galaxies, has been a quiet but constant part of its growth for billions of years. Every thin line of stars in our halo and every jumbled group of stars circling in the dark tells the story of another meal in space. Today, we know that this constant gravity eating has formed the Milky Way's structure, from its wide halo to the streams of stars that move around it. The concept of galactic cannibalism first gained traction in the 1970s, when astronomers began noticing faint arcs of stars surrounding larger galaxies. These arcs, or stellar streams, didn't belong to any known spiral arms or clusters. Instead, they appeared as trails, cosmic fingerprints left behind by small galaxies torn apart by tidal forces. As observations improved, similar features were found in the Milky Way itself. The discovery was revolutionary. Our galaxy was still in the process of assembling itself. One of the clearest examples is the Sagittarius dwarf elliptical galaxy, currently being shredded by the Milky Way's gravity. This small galaxy, once a respectable collection of billions of stars, now stretches into a long, looping stream that wraps around our galaxy multiple times. First discovered in 1994, the Sagittarius dwarf provided direct evidence that the Milky Way is still eating. Computer models show that each time it passes through our galactic disk, tidal forces strip away more stars, spreading them along its orbit until the original galaxy is little more than a remnant. Another victim is the Canis Major Dwarf Galaxy, located only 25,000 light-years from Earth. It is one of the nearest and most disrupted of the Milky Way's satellites, so faint that its discovery in 2003 required careful analysis of stellar motion rather than visible imaging. Its stars have already begun merging into the outer disk, forming a vast, ring-like structure known as the Monoceros Stream. This ripple of stars circles the Milky Way's edge like the ghostly outline of a devoured companion. Farther out, dozens of other dwarf spheroidal galaxies orbit our Milky Way, each a potential future meal. Some, like Draco, Ursa Minor and Fornax, have survived so far, but bear clear signs of gravitational stress. Their outer stars are stretched, their orbits elongated, and their dark matter halos distorted. Over billions of years, these small systems will spiral inward, eventually dissolving into our halo and adding their mass to our growing collection. The Gaia Space Observatory has revolutionized our understanding of this ongoing process. By tracking the positions and motions of over 1 billion stars, Gaia has revealed intricate networks of stellar streams and substructures hidden within the Milky Way's halo. Many of these streams are the remains of long-destroyed dwarf galaxies or globular clusters. One particularly significant discovery was the Gaia Sausage Enceladus event, a massive merger that occurred about 10 billion years ago. Evidence shows that a galaxy roughly 1/5 the mass of the Milky Way collided with us early in our history, scattering its stars throughout the halo and thickening our galactic disk. That ancient collision may have triggered one of the most active periods of star formation in our galaxy's history. Each merger leaves behind chemical and dynamical signatures. The stars from cannibalized galaxies often have different metallicities, proportions of heavy elements, and orbital patterns than those born in the Milky Way. By analyzing these differences, astronomers can reconstruct the family tree of our galaxy, identifying which stars were native and which were immigrants from smaller systems. The halo, once thought to be a uniform sphere, is now known to be a mosaic of stellar remnants, each tracing back to a different long-lost galaxy. The process of galactic cannibalism isn't purely destructive, it also fuels creation. As dwarf galaxies are torn apart, their gas is funneled into the Milky Way, feeding new rounds of star formation. Their stars help build the outer halo, while their dark matter contributes to the gravitational stability of the entire system. In a sense, the Milky Way grows both physically and chemically with every merger, recycling the remains of its victims into something new. This cosmic consumption also explains the warped shape of our galaxy's outer disk. The gravitational tugs of orbiting dwarfs, especially the large and small Magellanic Clouds, distort the Milky Way's structure, creating ripples and asymmetries. Recent studies using radio telescopes like ALMA and Meerkat have shown that even small companions can generate large-scale waves through the galactic disk as they orbit. These gravitational interactions act like a stone dropped into water, sending ripples through the stars and gas. The Milky Way itself is a product of this same cycle. Long before it became the grand spiral we see today, it was likely a swarm of smaller protogalaxies merging under gravity's influence. That assembly process never truly ended, it merely slowed. And in billions of years, when Andromeda finally collides with us, will play the role of the larger predator, absorbing another major galaxy in the same way we once consumed dwarfs. Stellar streams, the ghostly remains of galactic meals. Far above the plane of the galaxy, past the spiral arms and the bright center of the Milky Way, there are quiet rivers of stars moving through the darkness. These are star streams, which are the leftover pieces of galaxies and clusters that the Milky Way has broken up over billions of years. They can't be seen with the naked eye, but to current telescopes and space labs, they look like a thin skeleton that shows how our galaxy is structured gravitationally, which we can't see. It shows that the Milky Way has grown by eating other galaxies over a long period of time. Each stream is both a scar and a mark. The concept of stellar streams first emerged in the late 20th century, when astronomers studying star distributions noticed faint, linear overdensities, thin trails of stars that did not belong to the Milky Way's spiral arms or globular clusters. These weren't random alignments. Their stars moved in coordinated orbits, as though part of a single shredded system, Early examples included the Sagittarius Stream, Palomar 5 Stream, and GD1, each tracing enormous arcs around the galaxy, some stretching over 100,000 light-years in length. The Sagittarius Stream remains the most dramatic. Born from the Sagittarius dwarf elliptical galaxy, it wraps around the Milky Way in multiple loops, forming a kind of stellar ribbon that encircles our entire galactic disk. When the Sagittarius dwarf first entered the Milky Way's gravitational field billions of years ago, tidal forces began pulling it apart. Each pass around the galaxy stripped more of its stars, spreading them into a looping trail that still circles the sky today. Observations using the Gaia mission and Sloan Digital Sky Survey, SDSS, have mapped this stream in exquisite detail, revealing multiple layers of stellar debris and even secondary loops, evidence that the process has been ongoing for eons. The GD1 stream is a further noteworthy example. It is a much smaller and more fragile structure made up of old stars that used to be part of a globular cluster. A globular cluster does not have a dark matter ring to protect it like a galaxy does. When it got close to the heart of the galaxy, the Milky Way's tides pushed it apart, leaving a thin line of stars that is about 30,000 light-years long. Gaps, or small holes in the otherwise smooth path, are what make GD1 so interesting. These holes may have been made by dark matter groups that we can't see. They give us a rare, indirect look into the structure of the Milky Way's dark background. The Palomar 5 stream tells a similar story. Originating from a star cluster about 80,000 light-years away, it stretches across 1/3 of the sky in faint, thread-like arcs. Astronomers using data from Hubble and Gaia have confirmed that it is slowly dissolving, its remaining stars trickling away with each orbit. The cluster at its core is now so depleted that it may vanish completely within the next few 100 million years, leaving only the stream behind as its tombstone. Each stellar stream acts like a seismograph of gravity. As it orbits through the galaxy, it records subtle distortions in its shape and motion, evidence of the Milky Way's unseen components. By studying their curvature, speed, and distribution, astronomers can map the galaxy's gravitational potential, revealing where dark matter is concentrated and how it shapes the Milky Way's form. This technique has become one of the most precise ways to study our galaxy's invisible halo. But stellar streams are more than remnants. They are active probes. Their patterns allow scientists to detect disturbances caused by dark matter subhalos, small invisible clumps predicted by cosmological simulations. If one of these dark matter clumps passes near a stream, it creates a gravitational ripple, displacing stars and creating a kink or gap. By measuring these disruptions, astronomers can infer the presence, mass, and even distribution of dark matter around our galaxy. This method, sometimes called galactic archaeology, lets researchers study invisible structures on scales impossible to observe directly. Stellar streams also provide time capsules from the early universe. Many of their stars are ancient, over 10 billion years old, and contain very low metallicity, meaning they formed when the universe was young and heavy elements were scarce. By analyzing their chemical compositions, scientists can learn about the environments in which their parent galaxies or clusters formed, long before they were assimilated into the Milky Way. In some cases, stellar streams intersect with the galactic disk, passing through regions of higher density. When this happens, the gravitational interaction can distort both the stream and the disk, creating oscillations or ripples that persist for millions of years. These interactions help explain the subtle vertical waves recently observed in the Milky Way's outer disk, signatures of ancient encounters with satellite galaxies. The outer halo, the galaxy's farthest frontier. If the Milky Way were a city of stars, the outer halo would be its forest. It's a nearly empty area that stretches hundreds of thousands of light-years from the center of the galaxy, where gravity weakens and sunlight blends into the background. This area was once thought to be empty, but it turns out to have a lot of structure: faint stellar streams, scattered globular clusters, and old remnants from when the galaxy first started to join. From this spot on the edge of the Milky Way, scientists can finally see how big our galaxy really is. The concept of a galactic halo has existed for over a century, but only recently have we begun to resolve its full extent. Early astronomers believed the Milky Way's disk simply faded into interstellar space around 50,000 light-years from the center. Today, thanks to data from the Gaia space telescope, deep sky surveys, and powerful instruments like Subaru and CFHT, we now know the stellar halo stretches much farther, possibly out to 500,000 light-years or more, nearly halfway to the Andromeda galaxy. If we could see the Milky Way's true shape from afar, its luminous spiral disk would appear as a tiny core surrounded by a vast, ghostly sphere of scattered stars. This outer halo is made of two main components: an inner halo, more tightly bound to the galaxy, and an outer halo, where stars move in chaotic, elongated orbits that often take them far beyond the galactic plane. The difference between the two reveals the Milky Way's violent past. The inner halo likely formed from early mergers with a few relatively massive dwarf galaxies, while the outer halo was built from countless smaller ones, each contributing a handful of stars that now drift freely through space. Many of the halo stars are among the oldest in the galaxy, dating back more than 12 billion years. They contain almost no heavy elements, meaning they were born when the universe was still young and chemically primitive. These ancient stars serve as fossils of the Milky Way's infancy, preserving clues about the conditions that existed before the spiral disk even formed. Studying them helps astronomers reconstruct the sequence of mergers that built our galaxy, layer by layer. The outer halo is also where we find many of the Milky Way's globular clusters, dense, spherical swarms of hundreds of thousands of stars. Some, like Palomar 4 and NGC 2419, orbit at staggering distances of over 300,000 light-years. They move on paths so wide that they take billions of years to complete a single orbit. Others, like Eridanus II, may not be native at all, but captured from smaller galaxies during ancient mergers. These clusters act as gravitational probes, allowing scientists to measure how mass, and by extension, dark matter, is distributed far beyond the visible disk. The halo isn't just a collection of isolated stars and clusters. It also contains faint, thread-like structures, the remnants of dwarf galaxies long since torn apart by the Milky Way's gravity. These stellar streams, detected in surveys like SDSS, PAN-STARRS, and DES, reveal that the outer halo is still evolving. Each new stream discovered helps refine our understanding of how far the Milky Way's influence truly reaches. Some of these streams trace loops that extend more than 100,000 light-years beyond the galactic plane, suggesting that the Milky Way's gravitational field stretches farther than previously believed. The unevenness of the upper ring is one of the most intriguing characteristics about it. The halo doesn't look like a perfect sphere, it looks crooked, with different volumes going in different directions. Computer models show that this unevenness might be due to recent merging, like the Sagittarius dwarf galaxy's ongoing movement, or the Large Magellanic Clouds, LMC, pulling on it. Even though it is a neighbor galaxy, the LMC is so big that it bends the Milky Way's dark matter ring as it moves around it, leaving behind waves and wakes that are hundreds of thousands of light-years long. Observations of the halo also help answer one of astronomy's biggest puzzles, the so-called missing baryon problem. For decades, scientists noticed that galaxies like ours seem to contain less visible matter than expected from cosmological models. The discovery of the extended halo of hot, ionized gas, detected in X-rays and ultraviolet absorption lines, has solved much of that mystery. The outer halo holds an enormous reservoir of diffuse material, possibly containing half of the galaxy's ordinary matter. Though nearly invisible, this gas connects the Milky Way to the intergalactic medium, forming a bridge between our galaxy and the larger cosmic web. The halo's outermost reaches blur the boundary between galaxies. The Milky Way's dark matter halo, stretching nearly 2 million light-years, likely overlaps with that of Andromeda. This means the two galaxies are already gravitationally connected, their halos merging long before their visible disks will collide. In this sense, The future Milky Way-Andromeda merger has already begun in slow motion. The local group, the Milky Way's galactic family. The Milky Way isn't the only thing moving through space. The local group is a group of more than 50 galaxies that are pulled together by gravity and form a gravitational neighborhood. This small area of space, which is about 10 million light-years across, is home to our nearest galactic family. It's a dynamic system where spiral galaxies like the Milky Way and Andromeda rule, while smaller galaxies circle like distant cousins. Astronomers study this group to learn more about how galaxies grow, change over time, and interact on the largest sizes, which determine the structure of the universe itself. At the heart of the local group lie its two largest members, the Milky Way and the Andromeda Galaxy, M31. Each contains hundreds of billions of stars, massive dark matter halos, and systems of orbiting satellites. Together, these two giants account for more than 95% of the local group's total mass. Between them lies the smaller but still significant Triangulum Galaxy, M33, a graceful spiral roughly half the size of the Milky Way. Astronomers believe Triangulum may be gravitationally bound to Andromeda, possibly orbiting it as a satellite. This trio, Andromeda, the Milky Way, and Triangulum, forms the core of the local group's structure. Surrounding these major galaxies is a swarm of dwarf companions, most of them orbiting the larger two. The Milky Way alone hosts at least 60 known satellite galaxies, though faint ones are still being discovered. Some, like the large and small Magellanic Clouds, are easily visible from the southern hemisphere, two glowing patches of light just outside our galactic disk. Others, such as Draco, Ursa Minor, Sculptor, and Fornax, are much smaller and fainter, detectable only with sensitive instruments. Many of these dwarfs are so dim that they contain only a few thousand stars, yet they help scientists trace the gravitational contours of our galaxy's halo. Andromeda has an even richer entourage, with more than 100 dwarf galaxies orbiting within its domain. Some, like M32 and M110, are visible in small telescopes as tiny elliptical companions. Others are being actively torn apart, forming streams of stars that wrap around Andromeda's halo, mirroring the kind of cannibalism taking place in our own galaxy. The distribution and movement of these dwarfs provide crucial data about the total mass and extent of both galaxies' dark matter halos. Between the Milky Way and Andromeda lies a region known as the local group barycenter, the gravitational midpoint where the pull of both galaxies balances out. This point isn't fixed. It drifts slowly as the two galaxies move toward each other on their collision course. Roughly 4.5 billion years from now, the barycenter will cease to exist as a separate point when the two galaxies finally merge into a single larger system. Beyond these immediate members, the local group extends outward to include smaller associations of galaxies such as the NGC 3109 subgroup and the Leo 1 group. Some of these fringe galaxies are right on the edge of the local group's gravitational reach. In a few billion years, as the Milky Way and Andromeda merge and their combined gravity strengthens, many of these distant members will likely be captured, swelling the local group into an even larger system. The boundaries of the local group are defined not by visible structures, but by gravity itself. The outer edge, known as the zero-velocity surface, marks the point where the expansion of the universe overtakes the local group's gravitational pull. Beyond this radius, roughly 5 million light-years from the Milky Way, galaxies are receding faster than our collective gravity can hold them. Inside this boundary, however, everything remains gravitationally bound. The local group, therefore, acts as a tiny oasis of order amid the cosmic expansion, a miniature gravitational island in an ever-growing universe. Our group is not by itself. It is on the edges of the Virgo supercluster, a much bigger structure with thousands of galaxies spread out over 110 million light-years. The Milky Way and Andromeda both move around in one of the filaments of the Virgo supercluster. A filament is a long, thin line of galaxies and dark matter that connects other clusters in the cosmic web. the Virgo supercluster, our greater galactic environment. If the Milky Way and Andromeda are like a close family, then the Virgo supercluster is like the broader family. It is a huge city in space made up of thousands of galaxies spread out over 110 million light-years. It's the gravitational district to which our local group belongs. It's one of many groups that are linked by the cosmic web's unseen threads. This huge structure shows where our galaxy really is in the universe. It's in this area that gravity and growth are competing to shape the final structure of the universe. The Virgo supercluster takes its name from its largest and most massive concentration of galaxies, the Virgo cluster, located about 54 million light-years from Earth in the direction of the constellation Virgo. This cluster alone contains over 2,000 galaxies, bound together by an immense cloud of hot gas and dark matter, with a total mass exceeding 10 to the power of 15 solar masses. In its heart lie giant elliptical galaxies like M87, whose central black hole was famously imaged by the Event Horizon Telescope in 2019. These colossal galaxies are ancient and red, their shapes the result of countless mergers over billions of years. Surrounding them are spirals, lenticulars and dwarfs, all caught in a gravitational web that constantly churns and evolves. Our Milky Way, however, sits far from this dense core. We occupy a quieter region near the edge of the supercluster, embedded within a small filament known as the local sheet, a relatively flat arrangement of galaxy groups, including the local group, the Maffei group, and the Centaurus A group. These smaller associations orbit the Virgo cluster's massive gravitational center, just as moons orbit a planet, though on scales so large that their motions take billions of years to complete. For much of the 20th century, astronomers thought of the Virgo supercluster as a distinct, isolated structure, an island of matter in an expanding universe. But modern observations have revealed that it's merely one region within a much larger entity, the Laniakea supercluster. Hawaiian for immense heaven, Laniakea encompasses not only the Virgo supercluster, but several adjacent clusters and filaments, stretching across 520 million light-years and containing roughly 100,000 galaxies. In this grander view, Virgo is just one dense knot in a cosmic web of even larger proportions. The discovery of Laniakea came in 2014, when astronomers used precise galaxy motion maps to trace how gravity shapes their paths. Instead of moving randomly, galaxies follow streams that converge towards gravitational centers, regions of higher mass concentration. By identifying these flow patterns, scientists could map where one supercluster ends and another begins. The analysis showed that the Milky Way and its neighbors are being drawn toward a massive gravitational focal point deep within Laniakea, a region known as the Great Attractor. Within the Virgo supercluster itself, gravity and cosmic expansion are locked in a delicate tug-of-war. On small scales, within clusters and groups, gravity dominates, keeping galaxies bound together. But on the largest scales, the Hubble expansion takes over, causing space itself to stretch and carry galaxies apart. The transition point lies around 100 million light-years, roughly the boundary of the Virgo supercluster. Inside this radius, galaxies move toward each other. Beyond it, the universe's expansion pulls them away faster than gravity can reel them back in. The filamentary structure of the Virgo supercluster is another clue to the universe's grand design. Galaxies aren't evenly distributed through space. They form vast filaments and walls separated by immense voids. The Virgo filament connects our local group to the Virgo cluster through a chain of smaller groups and clusters, including the Leo cluster and Coma Berenices cluster. These structures act like cosmic highways, channeling the flow of galaxies, gas and dark matter along preferred directions. It's along these filaments that galaxy formation is most active, as matter continually falls inward under gravity's pull. Astronomers studying the Virgo supercluster also use it to understand the evolution of galaxies across different environments. In the cluster's dense core, galaxies are often stripped of gas through interactions with hot intracluster plasma, a process called ram pressure stripping. leaving them red, dead, and unable to form new stars. In contrast, galaxies like ours, on the outskirts of the supercluster, remain gas-rich and star-forming. By comparing these populations, scientists can observe how the environment determines a galaxy's fate. The Virgo supercluster also provides an anchor for the cosmic distance scale, the ladder astronomers use to measure the size of the universe. Variable stars, supernovae, and redshift measurements within Virgo have long been used to calibrate distances to more remote galaxies. These data underpin our understanding of cosmic expansion and the Hubble constant itself. Even though it is very big, the Virgo supercluster isn't always the same. It will keep changing shape over the next few billion years because of gravity. The Virgo cluster has a lot of gravity, and it will slowly pull in groups nearby, like the local group and Milky, which will be left over after the merger. Simulations show that in a very long time, trillions of years from now, the whole Virgo supercluster might come together to form a single huge elliptical structure, or supergalaxy, ringed by the dying remains of its smaller partners. The Great Attractor, the hidden force guiding our galaxy's motion. The Milky Way, Andromeda, and all the other galaxies close to us are not just floating around in space. They're quickly moving towards something. Astronomers call it the Great Attractor. It is a huge, unseen gravitational anomaly that pulls whole groups of galaxies, like the Virgo supercluster, toward it at hundreds of kilometers per second. It is one of the most mysterious things we know about the universe. It is a cosmic sink of gravity that is partly hidden by the thick plane of our own Milky Way. The existence of the Great Attractor was first suspected in the late 1970s, when astronomers began measuring the peculiar velocities of galaxies, their motion relative to the expanding universe. According to Hubble's law, galaxies farther away should recede faster, with their redshifts increasing linearly with distance. But when researchers looked at hundreds of galaxies in different directions, they noticed a pattern. Many were moving toward a specific region of the sky in the constellations Centaurus and Hydra, rather than simply expanding outward. Something massive, located about 150 to 250 million light-years away, was pulling them off course. The problem was visibility. The suspected region lies directly behind the zone of avoidance, the thickest part of the Milky Way's disk, where interstellar dust and stars obscure our view in optical light. For decades, it was impossible to observe what lay beyond. Only in the 1990s, with the development of infrared and radio surveys, did astronomers begin to peer through the veil. What they found was astonishing. An enormous concentration of mass stretching across tens of millions of light-years, anchored by a cluster of galaxies known as the Norma cluster, Abell 3627. Our local group, the Virgo cluster, and even other distant clusters are all being drawn toward this region at roughly 600 kilometers per second, about 1.3 million miles per hour. This motion is superimposed on the universe's general expansion, meaning that even as space itself stretches, local gravity pulls everything toward the same mysterious center. But what exactly is the Great Attractor? Its true nature remains under investigation. Some scientists suggest it's not a single object, but a gravitational basin, a dense node in the cosmic web where several massive superclusters intersect. Others believe it's part of an even larger structure known as the Shappley supercluster, located farther beyond Norma. The Shappley supercluster, discovered in the 1930s but fully mapped only recently, is a gargantuan complex containing over 8,000 galaxies and weighing the equivalent of 10,000 Milky Ways. Its gravitational pull may contribute significantly to the flow of galaxies in our region of space. Together, the Great Attractor and the Shappley supercluster represent one of the largest known concentrations of mass in the observable universe. Their combined gravitational influence extends across hundreds of millions of light-years, shaping the large-scale motion of entire galaxy clusters. Astronomers studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang, have confirmed this by detecting a subtle temperature dip called the CMB dipole anisotropy. It shows that the Milky Way itself is moving relative to the CMB at about 630 kilometers per second, directly toward the region of the Great Attractor. Mapping this gravitational landscape has required multiple generations of telescopes and data. Surveys such as 2MASS, HIPAS, and cosmic flows have traced galaxy distances and velocities across previously hidden regions. Each new dataset refines our picture of how matter is distributed beyond the zone of avoidance. The results reveal that the Great Attractor is not a singular point, but part of a vast gravitational gradient, an extended ridge of density stretching into the Shappley region. In essence, we're sliding down a cosmic slope. Even more intriguing is that the Great Attractor might not be static. Over cosmic time, the gravitational focus may be shifting toward Shappley, which lies another 200 million light-years beyond. This suggests that the flow of galaxies, including our own, could eventually align toward that larger mass concentration, making Shappley the ultimate center of gravity for our section of the universe. Despite decades of study, huge uncertainties remain. Because we're located inside the Milky Way's obscuring plane, our observations will always be incomplete. Many galaxies behind the dust remain undetected, and the full mass distribution is still being modeled. Yet, one thing is certain. The Great Attractor's pull affects every galaxy within hundreds of millions of light-years, defining the motion of our cosmic neighborhood. To conceptualize it, picture a huge gravity-shaped environment in space. It looks like the Milky Way and its neighbors are like marbles rolling along an unseen surface, following the curves and dips made by huge groups of galaxies. We are slowly going down one of these hills toward a secret valley that is unbelievably deep. The Shappley supercluster, the deeper source of the cosmic pull. Further along the same cosmic way as the Great Attractor, there is an even bigger and denser structure. It is so huge that it may be the real source of the gravitational pull that controls the motion of our whole galaxy. This is the Shappley supercluster, a huge grouping of matter that can be found in the constellation Centaurus, about 650 million light-years away. The Shappley supercluster is one of the biggest structures ever found in the visible universe. It is made up of more than 8,000 galaxies spread out over several groups. The Shappley supercluster was first identified in 1930 by astronomer Harlow Shapley, the same scientist who measured the size of the Milky Way and discovered our position far from its center. When he observed this patch of sky, Shapley noticed an unusually high density of galaxies in a single region, far more than typical background levels. But at the time, distances were poorly understood, and the true scale of the discovery wasn't clear. Decades later, as astronomers mapped redshifts and velocities, it became apparent that Shapley had found not a simple cluster, but an entire supercluster of clusters, stretching over 600 million light-years and weighing more than 10 quadrillion solar masses. At its core lies the Abell 3558 cluster, surrounded by several other massive clusters, including Abell 3556, Abell 3560, and Abell 3571. Each of these is a gravitational city in its own right, containing thousands of galaxies bound together by dark matter and hot intracluster gas. The entire Shappley complex is connected by filaments of galaxies and gas, forming an intricate cosmic network that glows faintly in X-rays and microwave emissions. Its gravity dominates a vast region of space, so large that it influences not only the Great Attractor, but also the flow of galaxies in surrounding superclusters. When astronomers began studying the peculiar velocities of galaxies in the late 20th century, they realized that the Great Attractor alone couldn't account for all observed motions. Some galaxies beyond its region weren't slowing down after passing it, as gravity would predict. They were still accelerating towards something farther away. This observation led scientists to propose that the Shappley supercluster was acting as an even deeper gravitational anchor, the true center of mass for our entire section of the cosmic web. Evidence supporting this came from the cosmic flow surveys, which measured the motion of thousands of galaxies relative to the cosmic microwave background. The results revealed that the entire Laniakea supercluster, including the Milky Way, Virgo, and the Great Attractor region, appears to be falling toward the Shappley concentration. In effect, the Shappley supercluster may be the ultimate destination of our galaxy's long gravitational journey, a journey that will take billions of years and never truly end. The Shappley supercluster's gravitational power is staggering. Its estimated mass, around 10 to 16 solar masses, makes it about 10 times heavier than the Virgo cluster and dense enough to influence galaxies hundreds of millions of light years away. In X-rays, telescopes like ROSAT and XMM Newton reveal vast clouds of hot plasma between its clusters, heated to tens of millions of degrees as galaxies fall inward. These glowing filaments form a kind of gravitational highway, channeling matter into the densest nodes over cosmic time. Computer simulations of large-scale structure formation show that superclusters like Shappley represent the largest coherent structures gravity can create before the expansion of the universe overcomes its pull. They are the cosmic equivalents of mountain ranges, dense, immovable peaks in a landscape of expanding space. Beyond them, the accelerating force of dark energy prevents any further large-scale assembly. In that sense, the Shappley supercluster marks the boundary between regions still governed by gravity and those now dominated by cosmic expansion. Astronomers studying Shappley have also noticed something remarkable. It's not symmetrical. The supercluster's mass is unevenly distributed, forming multiple overlapping components rather than a single spherical core. These substructures are still merging, producing shocks, X-ray emissions, and gravitational lensing effects. The region is a cosmic construction zone, a place where galaxies and clusters are still coalescing into larger entities. In this sense, Shappley offers a glimpse of the universe's ongoing evolution, where the web of matter is still tightening even as cosmic expansion stretches it apart. Scientists had to change their earlier maps of how the universe moves after they learned about Shapley's huge impact. What we used to call the Great Attractor might only be a foreground concentration, a smaller gravity feature on top of the bigger flow toward Shappley. The Great Attractor is like a stepping stone in a much bigger gravity current that starts close to our group and goes all the way to the center of the Shappley complex. The cosmic web, the universe's vast network of galaxies. From billions of light years away, the universe shows its secret structure. It's not just a bunch of galaxies spread out in a random pattern. It's a complex web of galaxies that spans the whole visible universe. This web is made up of strands of dark matter, gas, and galaxies that connect to make a lattice that spans the entire universe. There are also huge holes, which are areas that are so empty they don't hold much at all. It's so big that the Milky Way, Andromeda, the Virgo supercluster, and even the Shappley concentration are just tiny threads in it. The concept of the cosmic web emerged in the 1980s, when powerful computers first simulated how matter evolved after the Big Bang. Starting from tiny fluctuations in the early universe's density, minute ripples visible in the cosmic microwave background, CMB, scientists watched how gravity amplified these irregularities over billions of years. Denser regions drew in more material, while emptier regions emptied further, creating the first stars, galaxies, and clusters. What emerged in those simulations was astonishing. The universe formed not as a uniform expanse, but as a complex, interconnected network of filaments and knots. The filaments of this web act like highways for matter. They span hundreds of millions of light years, channeling gas, galaxies, and dark matter into dense nodes where galaxy clusters form. Between these filaments lie the cosmic voids, vast, bubble-like expanses tens or even hundreds of millions of light-years across, containing just a handful of galaxies, or none at all. These voids are the emptiest regions known in the universe, some with densities less than 1% of the cosmic average. Over the decades, observations confirmed that these simulations reflected reality. Surveys like the CFA Redshift Survey in the 1980s and later projects such as Sloan Digital Sky Survey, SDSS, and 2DF Galaxy Redshift Survey map the positions of millions of galaxies. When plotted in 3 dimensions, the distribution matched the predicted pattern perfectly. Long filaments of galaxies connecting dense clusters, surrounding enormous, nearly spherical voids. The largest single structure discovered, the Hercules Corona Borealis Great Wall, stretches more than 10 billion light-years, so enormous that it spans nearly 1/10 of the observable universe. Dark matter is at the center of this system. It supports the whole cosmos web without being seen. Light can't see dark matter, which makes up about 85% of all matter in the world. And because of its gravity, galaxies form and move in certain ways. Normal matter, like gas and dust, moves along dark matter strands. Where density levels peak, normal matter cools and collapses into galaxies. Galaxies like the Milky Way would not have been able to come together without dark matter's gravitational pull. Each filament of the cosmic web contains a mixture of galaxies, hot plasma, and dark matter bound together across unimaginable distances. Observations from X-ray telescopes and ultraviolet spectrographs have revealed the presence of the warm-hot intergalactic medium, WIM, a tenuous gas that fills the spaces between galaxies, heated to millions of degrees as it falls into filaments. This WIM may contain the universe's missing baryons, the ordinary matter unaccounted for in earlier measurements. The cosmic web, therefore, is not just a structure of galaxies. It's the reservoir of all matter, both visible and invisible. The intersections of filaments form nodes, where multiple streams of matter converge. These nodes give birth to massive galaxy clusters like Virgo, Coma, and Shappley, each sitting at a junction where gravity has gathered tremendous amounts of material. The Milky Way and its neighbors reside within one such filament, part of the Laniakea supercluster, which flows toward the gravitational basin centered near the Great Attractor and Shappley regions. The voids, though seemingly empty, play an equally important role. They expand faster than the universe's average rate, pushing matter outward toward the filaments and helping to shape the web's pattern. Galaxies near the edges of these voids experience a kind of gravitational push, which influences their velocity and can even alter large-scale cosmic flows. Astronomers study these motions to better understand the balance between gravity and the mysterious force of dark energy, which drives the universe's accelerated expansion. What makes the cosmic web remarkable is not just its size, but its connectivity. Across billions of light-years, the same structure repeats itself: filaments, nodes, voids, like a cosmic fractal. From the distribution of galaxies to the clustering of dark matter, everything follows the same underlying physical laws. Even on the scale of the Milky Way, local filaments of gas and dark matter reflect the same patterns found in the universe at large. The web structure, therefore, is self-similar. The universe looks roughly the same whether viewed from a distance of 1,000,000 or 1,000,000,000 light-years. The birth of the Milky Way. From primordial clouds to a galactic disk. Before the Milky Way's beautiful curving arms and its stars lit up the night, the universe was just a sea of hydrogen, helium, and dark matter with no shape. About 13.8 billion years ago, the Big Bang filled space with radiation and gas that were almost all the same. The only change in mass was a tiny 1 part in 100,000. Today, these tiny bumps in the cosmic microwave background are being studied. They were the starting points for galaxies like ours to grow. As the universe expanded and cooled, gravity began to amplify these initial density variations. Slightly denser regions attracted more material, slowly collapsing into clumps of dark matter called halos. These halos became the scaffolding for all future galaxies. Gas from the surrounding intergalactic medium flowed into them, cooling and condensing to form the first stars. Around 200 million years after the Big Bang, the first generation of stars, known as population 3 stars, ignited. They were massive, short-lived, and composed almost entirely of hydrogen and helium, since heavier elements had not yet been forged. When they exploded as supernovae, they enriched their surroundings with the first traces of carbon, oxygen, and iron, elements that would later form planets, life, and everything we know. The Milky Way's earliest ancestor likely began as a small protogalactic fragment, one of many in a region of space where dark matter density was slightly higher than average. Over hundreds of millions of years, these fragments merged under gravity, forming larger and larger systems. This chaotic era of assembly was violent. Galaxies collided, stars were flung into intergalactic space, and gas clouds compressed into new generations of stars. Simulations suggest that by 12.5 billion years ago, the Milky Way's first recognizable structure, its protohalo, had formed, containing many of the old metal-poor stars we see today in our galactic halo. As mergers continued, angular momentum from infalling gas caused the forming galaxy to flatten into a rotating disk. This transformation took several billion years, with each merger adding mass, momentum, and complexity. The gas within the disk cooled and condensed into dense clouds, giving birth to waves of new star formation. This period saw the rise of what we now call the thick disk, an early component of the Milky Way composed of older stars orbiting in slightly tilted, puffed-up trajectories. Roughly 10 billion years ago, a major event, known as the Gaia Sausage-Enceladus merger, reshaped the young Milky Way dramatically. A large dwarf galaxy, roughly a fifth of our galaxy's mass, collided with the proto-Milky Way. The impact stirred its stars into chaotic orbits, heated the disk, and enriched the halo with new material. Many of the stars still found in the inner halo today were born in that ancient galaxy and assimilated during this merger. It was a turning point. The collision marked the end of the Milky Way's wild youth and the beginning of its more stable evolution. After this epoch of chaos, the Milky Way entered a quieter phase. Gas from the cosmic web continued to stream inward along dark matter filaments, replenishing the galactic disk and fueling star formation. Over time, the thin disk emerged, a younger, flatter component containing stars like our Sun. This thin disk became the dominant feature of the galaxy, stretching over 100,000 light-years and giving the Milky Way its familiar spiral shape. The spiral arms themselves are not permanent structures, but patterns created by density waves, regions of slightly higher gravity that compress gas as they move through the disk. When gas enters these waves, it collapses into new stars, creating bright bands of stellar nurseries that trace the arms. Between the arms lie older, redder stars, drifting in relative calm. The Sun, for example, orbits the galactic center about once every 230 million years, traveling between spiral arms over time. A dense bulge formed from the mergers of smaller galaxies and the migration of stars toward the core. Within this bulge, the galaxy's supermassive black hole, Sagittarius A star, grew from the accretion of gas and perhaps earlier black hole seeds. Around it, stars orbit at blistering speeds, marking the Milky Way's gravitational heart. By around 8 billion years ago, the Milky Way had reached a recognizable form, a barred spiral with a stable disk, a massive halo, and a growing system of satellite galaxies. Star formation remained intense for several more billion years, before gradually slowing to its current, calmer rate. Even now, though, the galaxy continues to evolve. It draws in gas from its surroundings, interacts with dwarf galaxies like the Magellanic Clouds, and occasionally absorbs new material from the intergalactic medium. The Milky Way's future: collision, evolution, and survival. The Milky Way may look calm today, its spiral arms turning in quiet majesty, but the forces that built it are still at work. Stars drift, gas clouds collide, and gravity continues its slow, steady pull. The galaxy is far from static. It's a living, evolving system, still changing with every orbit of its 200 billion stars. And its future, while long and complex, is already written in the motions of nearby galaxies. What awaits the Milky Way is a sequence of cosmic transformations, collisions, mergers, and an eventual slow fading into darkness. The most significant chapter in this future story is already in motion. Roughly 2.5 million light-years away, the Andromeda galaxy, M31, is speeding toward us at nearly 250,000 miles per hour. Astronomers using the Hubble Space Telescope and the Gaia mission have confirmed that this isn't a passing drift. Andromeda is on a direct collision course. In about 4 to 5 billion years, our galaxies will begin to merge, triggering one of the grandest events in the universe, the formation of a new supergalaxy. The first stages of this encounter will unfold slowly. As Andromeda approaches, its immense gravitational field will distort the Milky Way's spiral structure, pulling on our outer arms and sending long streams of gas and stars into intergalactic space. From Earth's perspective, if humanity or its descendants are still here, Andromeda will grow from a faint smudge into a dazzling full-sky spiral. Over the next few 100 million years, the two galaxies will begin to interpenetrate, their stars passing harmlessly through one another, while their dark matter halos and gas clouds collide violently. These interactions will ignite a burst of star formation. As clouds of hydrogen compress and shock under gravitational tides, new stars will flare into existence across both galaxies, temporarily increasing their brightness. This period will be brief on cosmic timescales, perhaps a few 100 million years, but spectacular as nebulae and clusters bloom across the night sky. Eventually, after several close passes, the Milky Way and Andromeda will fully merge. Their spiral arms will unravel, their distinct identities erased. The end result will be a vast, smooth, elliptical galaxy with little remaining structure, a cosmic blend often referred to as Milkomeda or Milkdromeda. This new galaxy will contain nearly 1 trillion stars, along with an enormous dark matter halo extending millions of light-years. The supermassive black holes from Sagittarius A star and Andromeda's central black hole will spin toward each other at its center, sending out strong gravity waves as they join together to form a single, bigger black hole. That terrible event will release as much energy as millions of supernovae, but it will happen in the middle of the new galaxy without making a sound. In the aftermath, Milkomeda will enter a long phase of gradual decline. With much of its gas consumed in starbursts or expelled by galactic winds, new star formation will slow dramatically. The youngest, brightest stars will live short lives and die, leaving behind long-lived red and yellow stars. Over time, the galaxy will fade, transforming from a blue active system into a red and dead elliptical galaxy. Our Sun, if it still exists, will witness little of this. Long before the merger, in about 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury and Venus and possibly consuming Earth. What remains will shrink into a white dwarf, cooling over trillions of years. By the time Milkomeda settles into equilibrium, the Sun will be a cold ember drifting through a galaxy very different from the one it was born in. But the story doesn't end with Milkomeda. The merged galaxy will continue to absorb smaller companions, including the Triangulum galaxy, M33, and other members of the local group. Over billions more years, gravity will draw these remnants inward, adding their stars to Milkomeda's growing population. Eventually, our entire local group will become a single, unified structure, an isolated island of stars cut off from the rest of the cosmos. That isolation will come from the universe's accelerating expansion, driven by dark energy. As space itself stretches faster and faster, distant galaxies and superclusters will move beyond the cosmic horizon, disappearing from view forever. In roughly 100 billion years, only the remnants of our local group, Milkomeda and its satellites, will remain visible. Beyond that, everything else will fade into unreachable darkness. Within Milkomeda, however, gravitational interactions will continue. Stars will wander through new orbits, clusters will merge, and black holes will consume stragglers. In the deep future, the galaxy will stabilize into a smooth, rounded mass of faint red stars orbiting an enormous black hole. Over trillions of years, even those stars will die, leaving behind only white dwarfs, neutron stars, and black holes, a silent city of relics. By 10 to the power of 15 years, gravity will slowly cause these remnants to drift apart. as stars are flung into intergalactic space through distant gravitational encounters. Eventually, Milkomeda itself will dissolve, its last traces stretching thin across a dark universe. The once bright home of humanity will fade into invisibility, leaving only the echo of its gravity imprinted on space-time. The fate of all galaxies. The long decline of cosmic light. The ultimate merging of the Milky Way with Andromeda is just a small part of a much bigger story in the universe. The universe is slowly becoming less bright. Even though galaxies look bright, active, and full of energy right now, their brightness is only a short part of the universe's history. One day, the age of light will come to an end. This is the time when galaxies glow and stars shine. After that, there is a slow fall into darkness that astronomers call the degenerate era. During this time, galaxies fade, stars die, and the universe itself gets cold and empty. To understand how this happens, we start with the energy that fuels every galaxy, star formation. Galaxies are like cosmic engines, converting hydrogen gas into starlight through nuclear fusion. But that fuel is limited. Over billions of years, stars consume hydrogen faster than it can be replenished. Gas clouds are heated by supernova explosions and expelled by galactic winds. Gradually, galaxies run out of raw material for new stars. The Milky Way, for example, forms only about 1 to 2 solar masses of new stars per year today, a fraction of the rate it sustained in its youth, nearly 10 times higher around 8–10 billion years ago. The decline is universal. Across the observable cosmos, the cosmic star formation rate peaked roughly 10 billion years ago, during what astronomers call cosmic noon. Since then, star birth has slowed by more than 90%. Galaxies that once glowed blue from newborn stars now shift toward yellow and red, dominated by older, cooler stellar populations. As time goes on, this slow reddening continues, until the universe's light becomes dominated by the faint glow of aging stars. In another 100 billion years, most galaxies will have exhausted their gas supplies completely. Only low-mass red dwarfs, small, cool stars that burn fuel very slowly, will remain. These stars can shine for up to 10 trillion years, but even their immense lifespans are finite. When the last of them flickers out, the universe will enter its twilight. At that point, galaxies will consist primarily of stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs, the burned-out cores of sun-like stars, will gradually cool and darken, becoming black dwarfs, cold, inert spheres invisible to any observer. Massive stars that ended in supernovae will leave behind neutron stars and black holes, orbiting quietly within the darkened remnants of their galaxies. Even without starlight, galaxies will remain dynamic for a long time. Gravity will continue to pull stars and remnants toward one another, occasionally forming new binary systems or merging compact objects. Over trillions of years, some stars will be ejected from their galaxies entirely through gravitational interactions, leaving behind a slowly shrinking core. Black holes will dominate these late cosmic structures, accreting the occasional stray object and growing ever so slightly larger. But another force is at work, one that will ultimately undo even the galaxies themselves: cosmic expansion. Driven by dark energy, the universe's expansion isn't slowing down, it's accelerating. Every second, the space between galaxies stretches faster than before. Over time, this expansion will isolate each gravitationally bound region from the rest. Within about 100 billion years, the universe will expand so much that galaxies beyond our local group will slip beyond our cosmic horizon, the distance from which light can ever reach us. By then, any observers still existing inside Milkomeda will see only a small pocket of light in an otherwise black sky. Every other galaxy, every other cluster will have disappeared, their light stretched to invisibility by the relentless expansion of space. This will mark the beginning of the cosmic isolation phase, when all remaining civilizations, if any exist, will be cut off from the larger universe forever. Inside the isolated remnants of galaxies, time keeps stretching. After about 10 to the power of 15 years, the orbits of stars will destabilize due to gravitational encounters, and many remnants will drift into intergalactic space. The once grand structures of galaxies will dissolve, leaving only scattered remnants orbiting massive black holes. By 10 to the power of 15 years, galaxies will no longer exist in any recognizable form. In the unimaginable epochs that follow, black holes will reign as the universe's dominant structures. They too are not eternal. According to Stephen Hawking's theory of radiation, black holes slowly lose mass by emitting tiny amounts of energy over immense timescales. The process is negligible now. A black hole the mass of the Sun would take 10 to the power of 67 years to evaporate. But across trillions of years, it becomes significant. Eventually, even the supermassive black holes at the centers of galaxies will vanish, releasing their last bursts of Hawking radiation into the void. After the last black hole evaporates, the universe will enter its final stage, the dark era. No stars, no galaxies, no light, only thinly scattered particles and fading radiation drifting through an ever-expanding cosmos. Temperature differences will vanish. Energy will spread so evenly that no process, not even the formation of new structures, can occur. This is known as the heat death of the universe, a state of perfect equilibrium where nothing more can happen. The dark matter halo, the invisible skeleton of our galaxy. There is something around every galaxy, even our own Milky Way, that we can't see, touch, or directly sense. But galaxies would not be possible without it. The dark matter halo is the name of this secret structure. It is a huge, unseen cloud of mass that goes far beyond the visible stars. It is the structure that holds everything together in our galaxy that we can't see. When astronomers first measured the rotation of galaxies in the 20th century, they found something strange. According to Newtonian physics, stars farther from a galaxy's center should orbit more slowly, just as planets in our solar system move slower the farther they are from the Sun. But when astronomers like Vera Rubin measured the rotation curve of the Andromeda galaxy in the 1970s, they found that stars far out in the galactic outskirts were moving just as fast as those near the center. That made no sense if all the mass was concentrated in the visible region. Something unseen had to be providing extra gravity to hold those fast-moving stars in orbit, an enormous amount of additional matter invisible to telescopes. This was the birth of the dark matter theory. Today, we know that roughly 85% of the total mass of the Milky Way consists of dark matter. The visible galaxy, with all its stars, planets, and nebulae, is only a thin slice within this massive spherical halo that stretches up to 2 million light-years across. That means our galaxy's true edge reaches nearly halfway to Andromeda. Unlike ordinary matter, dark matter does not interact with light or electromagnetic radiation. It does not glow, absorb, or scatter light. The only reason we know it exists is because of its gravitational influence. We see how it shapes the rotation of stars, bends light from distant galaxies through gravitational lensing, and affects the overall structure of the cosmos. Without dark matter, galaxies would spin themselves apart. Astronomers have spent decades trying to identify what dark matter actually is. The leading candidates are exotic, as yet undetected particles such as WIMPs, weakly interacting massive particles, or axions. These particles would have mass and exert gravity, but almost never collide with normal atoms, passing straight through planets, stars, and even our own bodies without leaving a trace. On Earth, experiments like Lux Zeppelin, Xenont, and Super CDMs are buried deep underground, shielded from cosmic radiation, waiting for a rare dark matter particle to interact with atomic nuclei. So far, none have been conclusively detected. Astronomers can map the dark matter halo indirectly. They use the motions of stars, globular clusters, and satellite galaxies to infer where gravity is strongest. These observations show that the Milky Way's dark matter halo is roughly 10 to 30 times more massive than all the stars and gas combined, weighing the equivalent of 1 to 3 trillion suns. the halo's density is highest near the galactic center and decreases smoothly with distance, fading into intergalactic space. Computer simulations of galaxy formation reveal that dark matter halos form first, collapsing under gravity long before stars ever ignite. They act as gravitational wells that pull in gas, giving shape to the galaxies that will form inside them. The visible Milky Way, with its spiral arms and bright bulge, is essentially a thin, rotating disk embedded within a massive invisible sphere. Without that stabilizing halo, the spiral structure could never have persisted for billions of years. The halo isn't static, though. It's constantly evolving as smaller dark matter clumps merge and dissolve. Some of these clumps may survive as subhalos, invisible mini-structures orbiting within the main halo. Astronomers think many of the Milky Way's small satellite galaxies, such as Draco and Fornax, sit within their own dark matter subhalos, gravitational cocoons that protect them from tidal destruction. The halo also interacts gravitationally with other galaxies. As the large and small Magellanic Clouds orbit the Milky Way, their motion stirs up waves in the halo, much like a stone disturbing the surface of a pond. These ripples may influence how gas flows into the galactic disk and how stars form over time. Some studies even suggest that our halo is slightly lopsided, perhaps stretched by the pull of the approaching Andromeda galaxy, or shaped by past collisions with smaller galaxies. A further intriguing fact about dark matter halos is that they show how the universe is put together. Astronomers use maps to show the big structure of the universe. The galaxies are grouped along walls and filaments that are divided by huge empty spaces. This pattern isn't just a coincidence, it's been shaped by dark matter's pull. Galaxies only form in places where there is a lot of dark matter, and they stick together in these unseen frames. Dark matter isn't just a supporting force in this way, it's the basic plan for the world. Dark energy, the force, stretching the Milky Way's future. Black holes push galaxies apart, but dark energy pulls them together. It makes everything fall apart. The universe is not only growing, it's speeding up because of this unknown force. The stars, planets, and ring of the Milky Way are still held together by gravity for now, but dark energy is already changing the galaxy's long-term fate in ways that are hard to understand. Astronomers first discovered dark energy by accident in the late 1990s. Two independent teams studying type Ia supernovae, standard candles used to measure cosmic distances, noticed that distant galaxies were dimmer than expected. That meant they were farther away than they should have been if the universe's expansion was slowing down under gravity. The only explanation was that the expansion was speeding up. Something unseen, acting against gravity, was driving galaxies apart faster and faster over time. This something was named dark energy. Today, we know that dark energy dominates the cosmos. It makes up about 68% of the total energy density of the universe. Dark matter contributes around 27%, and everything else, stars, gas, planets, and life, accounts for less than 5%. In other words, the force that determines the ultimate destiny of the Milky Way and all galaxies is something we barely understand and cannot observe directly. So what is dark energy? The leading explanation is that it's a property of space itself. According to Einstein's theory of general relativity, empty space can have energy. This idea is known as the cosmological constant, denoted by the Greek letter lambda. It suggests that space naturally exerts a repulsive pressure, counteracting gravity on large scales. As the universe expands, more space appears, and thus more of this energy fills the cosmos, driving even faster expansion. Some physicists believe dark energy could come from a slowly evolving scalar field known as quintessence, whose density changes over time. Others suggest that our understanding of gravity itself may need revision, that on cosmological scales, Einstein's equations might not fully describe how space-time behaves. Whatever the explanation, dark energy remains the single largest and least understood component of the universe. For galaxies like the Milky Way, the implications are profound. Right now, our galaxy is gravitationally bound to its neighbors in the local group, including Andromeda and the Triangulum galaxy. These systems are close enough that dark energy cannot pull them apart. Their gravity overcomes the cosmic expansion. But beyond this local region, space is stretching so rapidly that distant galaxies are racing away from us faster every day. In about 100 billion years, dark energy will have expanded the universe so much that no light from galaxies beyond our local group will ever reach us. The rest of the cosmos will fade from view, leaving the merged Milky galaxy, the future union of the Milky Way and Andromeda, adrift in an empty void. To any future observers within Milky, it will seem as though their galaxy is the only one that ever existed. The cosmic background radiation will have redshifted beyond detectability, and even the knowledge of an expanding universe may vanish. When you think of a harmful force, dark energy is not what you mean. It does not tear galaxies or atoms apart. Instead, it expands space-time itself. It has effects that are so incredibly small that not even the most sensitive tools on Earth can pick them up. But when you look at hundreds of millions of light years, you can't stop the effect from building up. At the moment, the rate of expansion of the universe is going up by about 74 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of distance, a galaxy's speed of contraction goes up by another 74 kilometers per s. The future depends on how dark energy behaves. If it remains constant, as Einstein's cosmological constant suggests, galaxies beyond our gravitational neighborhood will drift forever beyond our reach, and the universe will continue to expand exponentially into eternity. But if dark energy grows stronger over time, a more catastrophic fate, called the Big Rip, could await. In the Big Rip scenario, the expansion accelerates to the point that it overcomes all forces, even gravity at the galactic and atomic levels. First, galaxy clusters would separate. Then galaxies themselves would be torn apart. Finally, in the distant future, perhaps 20 to 30 billion years from now, even stars, planets, and molecules could be shredded as space expands faster than light can travel. The fabric of the universe would literally rip apart. The galactic neighborhood, hidden structures beyond the Milky Way. When we look up at night, the Milky Way is seen as a bright band that goes across the sky, but that thin line is just the start. Our galaxy is part of a much bigger and more complicated structure. It's part of a web-like pattern in space made up of galaxies, clusters, and strands. The Milky Way is just a small part of this huge cosmic web. It is connected to its neighbors by gravity and is ringed by dark matter and gas that you can't see. The immediate environment of the Milky Way is called the local group, a gravitationally bound family of more than 60 galaxies. The two dominant members are the Milky Way and Andromeda, M31, each surrounded by dozens of smaller satellite galaxies. The Triangulum galaxy, M33, is the third largest, orbiting near Andromeda, while tiny companions like the large and small Magellanic Clouds orbit the Milky Way itself. Most of the remaining members are dwarf spheroidal galaxies, small, faint systems containing only a few million stars, like the Draco, Fornax, and Sculptor dwarfs. The local group stretches roughly 10 million light-years across, and though that sounds enormous, it's actually one of the smaller galaxy associations in the universe. The entire group is bound together by the combined gravity of its dark matter halos. Within it, galaxies move relative to each other at speeds of hundreds of kilometers per second, tracing slow, looping orbits that take billions of years to complete. The Milky Way and Andromeda, for example, are currently closing the distance between them and will eventually merge in about 4-5 billion years, forming a single giant galaxy called Milky. But beyond the local group lies an even greater structure, the local sheet, a flattened collection of galaxy groups stretching over 50 million light-years. This sheet isn't just a random scattering of galaxies, it's a coherent plane embedded within the cosmic web. Gravity has drawn galaxies into this sheet over billions of years, compressing them into a thin layer bordered by vast cosmic voids, regions of near-empty space spanning hundreds of millions of light-years. The local sheet includes neighboring groups such as the Maffei group, the Sculptor group, and the IC 342 group, all gravitationally linked within the same large-scale flow. The local sheet itself belongs to a still larger structure. The local group's host supercluster, known as the Laniakea supercluster. Discovered in 2014 through detailed mapping of galaxy motions, Laniakea redefined our cosmic address. It encompasses more than 100,000 galaxies spread across 520 million light-years, including our own local group, the Virgo cluster, and many others. The word Laniakea means immense heaven in Hawaiian, an appropriate name for the gravitational basin that defines our region of the universe. At the heart of Laniakea lies the Virgo cluster, a massive collection of over 1,300 galaxies located about 54 million light-years away in the constellation Virgo. The cluster's gravitational pull influences the motion of the Milky Way and nearby groups, drawing us gently toward its center. Virgo itself sits along a filament that connects to even larger cosmic structures, including the Hydra Centaurus supercluster, the region that houses the mysterious Great Attractor we explored earlier. These interlinked filaments form part of the cosmic web, the grand architecture of the universe. The cosmic web is not an abstract idea. It's a real physical network of matter. Galaxies like the Milky Way trace its densest threads, while the spaces between them are filled with hot, thin gas known as the intergalactic medium. Observations from instruments like the Chandra X-ray Observatory and the Planck satellite have shown that these filaments contain a significant fraction of the universe's missing baryons, normal matter that escaped detection because it's spread too thin to emit visible light. These filaments are the highways along which gas flows, feeding galaxies and enabling new star formation over cosmic time. Within this structure, galaxies are not isolated objects, but participants in an ongoing exchange of matter and energy. The Milky Way, for instance, is constantly interacting with its environment. Streams of gas, such as the Magellanic Stream, connect our galaxy to the Magellanic Clouds, while faint stellar bridges link the Milky Way to distant dwarf galaxies it has torn apart. Even now, faint tidal streams, the remains of ancient mergers, weave through our galactic halo like ghostly fingerprints of past collisions. Understanding our galactic neighborhood helps astronomers trace the flow of cosmic matter. Using precise distance measurements and velocity data from the Cosmic Flows project, scientists have mapped how thousands of galaxies move within the local universe. These maps reveal that the Milky Way is drifting towards the Great Attractor region at about 600 kilometers per second, while the entire Laniakea supercluster itself moves toward the Shappley supercluster, an even larger gravitational concentration lying more than 600 million light-years away. This motion means that even though galaxies are bound within local groups and superclusters, they're still influenced by far larger cosmic currents, the gravitational tides of the universe itself. Our Milky Way, in a sense, is floating downstream in a river of galaxies, carried by invisible flows shaped by both dark matter and dark energy. In the future, studies using cameras like Euclid and the Vera Rubin Observatory will map these structures in a way that has never been done before. This will show how deeply our galaxy is linked to the cosmic web. Simulations on a computer already show that galaxies like the Milky Way don't just sit still in their halos. They move, spin, and grow along these strands, swapping gas and stars over billions of years. The hidden side of the Milky Way. Discoveries behind the galactic dust. Astronomers thought they knew what the Milky Way looked like for hundreds of years, a bright, wide river of stars that ran through the sky at night. But that point of view is wrong. From Earth, all we can see is a small part of the bigger picture. A lot of our galaxy is still hidden by thick clouds of cosmic dust that soak up and spread out visible light. Behind that veil is a huge unknown world full of places where stars are being born, groups of stars from long ago, and whole galaxy structures that were only recently discovered. The Milky Way's disk is full of dust lanes, cold, dense clouds made of carbon, silicates, and frozen gases. These grains are small, but they're efficient at blocking visible light. Even in the clearest, darkest skies, we can only see a few thousand light years into the plane of the galaxy before the light fades into obscurity. From Earth's position, roughly 26,000 light-years from the galactic center, much of the Milky Way's inner regions are invisible to optical telescopes. This makes mapping our own galaxy one of the most challenging tasks in astronomy. It's like trying to explore a forest while trapped beneath its canopy. The breakthrough came with infrared astronomy. Unlike visible light, infrared radiation can pass through interstellar dust with minimal absorption. When astronomers began observing the sky in infrared wavelengths using space telescopes such as IRAS, Infrared Astronomical Satellite, in 1983 and Spitzer Space Telescope in 2003, they discovered that the dark zones of the Milky Way were far from empty. Behind the dust lay vast nurseries of stars, glowing regions where gas clouds collapse under gravity to form new suns. In particular, Spitzer's GLIMPSE, Galactic Legacy Infrared Mid-Plane Survey Extraordinaire project, revealed the intricate structure of our galactic plane in exquisite detail. The survey uncovered giant molecular clouds, star clusters, and massive filaments of dust and gas snaking across thousands of light years. These are the engines of star formation, the hidden heartbeats of our galaxy. Infrared studies also confirmed a major structural feature that was invisible before, the central bar. For decades, astronomers debated whether the Milky Way had a bar-shaped concentration of stars stretching across its core, as many spiral galaxies do. Spitzer's infrared vision finally settled the question. It revealed a 27,000 light-year-long bar composed of old, densely packed stars extending through the galactic center. The bar acts as a gravitational engine, channeling gas inward to fuel star formation, and possibly feed the supermassive black hole at the core, Sagittarius A*. Beyond the bar lies the galactic bulge, a densely populated region filled with ancient stars and mysterious structures. Hidden deep within the dust, astronomers have discovered X-shaped stellar distributions and metal-rich populations that hint at a complex evolutionary history, likely the result of past mergers and internal dynamical shifts. The bulge, once thought to be a simple spherical cluster of stars, is now known to be asymmetrical and warped, like a cosmic hourglass glowing behind curtains of dust. But the Milky Way's disk's warp and flare may be the most compelling secret trait found in the last few years. Radio studies like Hi-4Pi and observations from the Gaia Space Telescope have shown that the edges of our galaxy are not flat. Instead, they bend and twist upward, making a wavy shape that spins slowly over time. The most likely reason: there are gravitational effects on the Large Magellanic Cloud, or changes in shape due to dark matter around us. The finding means that our galaxy is not a flat disk, but a moving, wavy structure that is always changing shape due to forces we can't see. Radio astronomy has also played a vital role in unveiling the hidden Milky Way. By studying neutral hydrogen, Hi, at a wavelength of 21 centimeters, scientists can map the structure of the galaxy even where visible light cannot penetrate. These radio surveys have revealed the full extent of the Milky Way's spiral arms, showing that our galaxy has at least 4 major arms: the Perseus, Sagittarius, Norma, and Scutum Centaurus arms, along with smaller spurs like the Orion arm, where our solar system resides. The Atacama Large Millimeter-Submillimeter Array, ALMA, has further deepened this view, allowing astronomers to zoom in on star-forming regions buried within the dust. ALMA's precision has uncovered dense cores of molecular gas that will eventually give birth to massive stars, the future beacons of the Milky Way. Even gamma-ray and X-ray observatories have joined the search. Instruments like NASA's Fermi Gamma-Ray Space Telescope have detected enormous bubble-like structures extending above and below the galactic plane, known as the Fermi bubbles. These colossal features, each spanning 25,000 light-years, are believed to be remnants of an energetic outburst from Sagittarius A* several million years ago. Their existence suggests that the Milky Way's central black hole was once far more active, behaving like a quasar, a revelation completely hidden from optical telescopes. Mapping the Milky Way, how we know its true shape. Because we live inside the Milky Way, it is one of the hardest things in science to figure out how it is put together. We can't just take a picture of our home galaxy from where we are, contained within the galactic disk and ringed by thick clouds of gas and dust. Over many years of careful study, smart guesswork, and the use of light at all wavelengths, from radio waves to gamma rays, we now know everything we know about the Milky Way's shape, size, and structure. The first attempts to map the Milky Way began long before the space age. In the 18th century, William Herschel, using a modest telescope, counted stars in different directions of the sky. He noticed that stars were concentrated in a flattened band, the Milky Way, and concluded that we lived inside a disk-shaped system. Though his model was crude and limited by dust extinction, it was humanity's first step toward understanding that our galaxy was a finite island of stars. A major leap came in the early 20th century with the work of Harlow Shappley, who used globular clusters, dense spherical groups of ancient stars, as tracers. By measuring their positions and distances, he realized that the center of the Milky Way was not near the Sun, as once thought, but located tens of thousands of light-years away in the direction of the constellation Sagittarius. Shapley's discovery displaced Earth from the galactic center, just as Copernicus had removed it from the center of the solar system. Still, visible light could only take us so far. The next revolution came with radio astronomy in the 1950s. Radio waves can penetrate the dust that blocks optical light, allowing astronomers to observe the distribution of neutral hydrogen, Hi, gas across the Milky Way. By measuring its 21-centimeter wavelength emission and combining it with Doppler shift data, the change in frequency due to motion, astronomers created the first detailed maps of the galactic spiral arms. These surveys revealed that our galaxy is not a uniform disk, but a barred spiral, with multiple arms winding around a central bulge. As technology advanced, astronomers began mapping the Milky Way in other wavelengths. Infrared telescopes like COBE, Spitzer, and WISE allowed us to see through the dust, revealing the dense star fields of the inner galaxy and confirming the presence of a bar structure about 27,000 light-years long. Infrared surveys also showed the warped, rippled edges of the galactic disk, distortions likely caused by gravitational interactions with nearby dwarf galaxies or dark matter clumps. The next major breakthrough came from the European Space Agency's Gaia mission, launched in 2013. Gaia is measuring the positions, motions, and distances of more than 1.5 billion stars with unprecedented accuracy, creating the first true three-dimensional map of the Milky Way. By tracking how stars move over time, Gaia has revealed the galaxy's dynamic nature, showing waves rippling through the disk, remnants of ancient mergers, and detailed evidence of spiral structure. It even identified the Gaia Sausage Enceladus event, a colossal collision between the Milky Way and another galaxy about 10 billion years ago, which helped shape our stellar halo. Gaia's data, when combined with spectroscopic surveys such as Apogee and LAMOST, has allowed astronomers to classify stars by their chemical compositions, effectively reconstructing the Milky Way's formation history. Stars with similar chemical fingerprints can be linked back to the same origin, letting scientists identify ancient stellar streams and the debris of long-absorbed dwarf galaxies. In parallel, radio and sub-millimeter observations continue to refine our view of the spiral arms. Surveys like Thor, the HI-OH recombination line survey, and Bessel, bar and spiral structure legacy, use masers, naturally amplified radio emissions from molecules like water and methanol, to precisely measure distances to star-forming regions. These data show that the Milky Way has four major spiral arms: the Perseus, Sagittarius, Norma, and Scutum Centaurus arms, connected by smaller spurs, including the Orion spur, where the Sun is located. The overall shape that emerges from all these studies is that of a barred spiral galaxy, about 100,000 light-years wide and 1,000 light-years thick. At its center sits a dense bulge of old stars, wrapped in a rotating bar of stellar material. From this bar extend long, curving spiral arms rich in gas and young stars. Surrounding the disk is a vast stellar halo, a spherical cloud of ancient stars and globular clusters stretching more than 100,000 light-years above and below the plane. Beyond even that lies the dark matter halo, extending to nearly 2 million light-years. New information suggests that the Milky Way is still getting bigger. Astronomers have found star streams using data from Gaia and other telescopes. These are the pieces of smaller galaxies that are being swallowed into our halo. These streams, which look like cosmic fingerprints, keep track of the galaxy's past of eating itself. The Sagittarius stream, one of the most important, wraps around the galaxy like a band. It is the last remnant of the Sagittarius dwarf galaxy, which is being torn apart by our gravity right now. The dance of galaxies, collisions and mergers across the cosmos. A lot of the time when we think of galaxies, we picture them as peaceful islands of stars floating in space. The universe really changes a lot more than that. Galaxies are always interacting with each other. They pull, hit and merge in a slow, beautiful and sometimes deadly dance that has been shaping the universe since the beginning. The Milky Way has been through this cosmic dance before. It has swallowed up smaller galaxies and is set to collide with a much bigger one in the future. Every galaxy, including ours, is surrounded by an extended gravitational field and an enormous dark matter halo. These halos overlap when galaxies come close, allowing them to feel each other's pull long before their stars ever touch. Once the attraction begins, their paths curve inward, and what follows can take billions of years. A dance choreographed entirely by gravity. When two galaxies approach, the first signs of interaction appear as tidal distortions. Their mutual gravity stretches and warps each other's shapes, pulling long streams of stars and gas into space called tidal tails. These tails can span hundreds of thousands of light years, glowing faintly as newly formed stars light up the debris. In some cases, these interactions trigger intense starburst events, where clouds of gas collapse rapidly to form millions of new stars. A classic example is the Antennae galaxies, located about 45 million light-years away. Once two separate spirals, they are now locked in a slow collision, their arms twisted into sweeping arcs that resemble insect antennae. In their overlapping region, young clusters of stars blaze to life, some of the most active star-forming zones ever observed. Similar events on a smaller scale have likely occurred in the Milky Way's past, and continue to happen even now. Our galaxy has absorbed numerous dwarf galaxies over billions of years. Evidence of these mergers can be found in stellar streams, faint trails of stars wrapping around the Milky Way's halo. One of the most prominent examples is the Sagittarius stream, the shredded remains of the Sagittarius dwarf elliptical galaxy, currently being torn apart by our gravity. These stellar streams act as cosmic fossils, preserving the history of the Milky Way's growth through galactic cannibalism. Simulations and observations suggest that our galaxy has undergone at least a dozen major mergers and hundreds of smaller ones since its formation. One of the most significant, called the Gaia Sausage Enceladus event, occurred around 10 billion years ago when a galaxy roughly 1/4 the Milky Way's mass collided with it. The impact heated and thickened our galactic disk, scattered stars into the halo, and contributed heavily to the Milky Way's present structure. Without that ancient collision, our galaxy would likely look very different today. These galactic encounters are not rare. In the nearby universe, astronomers routinely observe galaxies in various stages of merging. The Whirlpool galaxy, M51, for instance, owes its beautiful spiral arms to the gravitational influence of a smaller companion passing close by. The Mice galaxies, NGC 4676a and b, show two elegant, elongated tails formed by mutual tidal forces. Over the next few 100 million years, they will merge into a single, larger elliptical galaxy, a process mirrored countless times across the cosmos. When galaxies merge, their stars rarely collide directly. The distances between individual stars are vast, so they simply pass by one another. The real drama occurs in the gas and dark matter. Gas clouds slam together, compressing and forming new stars. The central supermassive black holes of each galaxy spiral toward each other, radiating gravitational waves as they close the distance. When they finally merge, they unleash bursts of energy that can be detected across the universe. The Milky Way's next major encounter will be with the Andromeda galaxy about 4 billion years from now. As Andromeda approaches, the two galaxies will distort each other, sending streams of stars flying into intergalactic space. Over several close passes, their spiral arms will unravel, their shapes will blend, and they will eventually form a single, enormous elliptical galaxy. The resulting system, nicknamed Milkomeda, will contain roughly 1 trillion stars and a supermassive black hole at its center, formed from the merger of Sagittarius A star and Andromeda's own central black hole. In the wider scheme of things, these impacts are very important to how galaxies change over time. Small galaxies join together to make bigger ones, and bigger ones join together to make huge ellipticals. Hierarchical growth is the name of this process, and it's how the organization of the universe changes over time. All galaxies, including the Milky Way and the Andromeda galaxy, are made up of galaxies that have merged with each other. This is a global process that is driven by gravity and led by dark matter. Measuring the Milky Way's mass, weighing a galactic giant. At first glance, it might look easy to figure out how big the Milky Way is. Just add up all the stars' weights. But galaxies are not neat places to live. Most of their mass is hidden by dark matter halos that go far beyond the stars that can be seen. One of the hardest things in modern astronomy is figuring out how much mass the Milky Way really has, because it is ringed by a huge dark disk that covers almost 2 million light-years. Early estimates of our galaxy's mass varied wildly because astronomers could see only part of the picture. In the early 20th century, astronomers calculated the combined mass of the Milky Way's visible stars to be roughly 100 billion solar masses. That was based purely on brightness, counting stars, and assuming their luminosity correlated with mass. But by the 1970s, when astronomers began studying how stars and gas rotate within the galaxy, it became clear that visible matter alone couldn't explain the observed motion. The stars in the outer regions were orbiting much faster than expected. If only visible mass existed, they would have flown off into space. Something unseen, dark matter, had to be adding gravitational weight. To determine these numbers, scientists use multiple techniques. One of the most reliable methods involves measuring orbital speeds. Just as the motion of planets around the Sun reveals the Sun's mass, the motion of stars, globular clusters, and satellite galaxies reveals the Milky Way's gravitational pull. Astronomers plot rotation curves, graphs showing how orbital speed changes with distance from the galactic center. For the Milky Way, these curves stay flat far beyond the visible edge of the disk, implying that mass continues to increase with distance, the telltale sign of dark matter's presence. A different method is to look at the paths of faraway globular clusters and companion galaxies, like the large and small Magellanic Clouds. The Milky Way's gravity makes these small partners move, and by keeping track of their speeds and paths, scientists can figure out how much mass must be in their orbits. These models have been improved by data from the Hubble Space Telescope and the Gaia mission, which has brought the Milky Way's total mass down to about 1.3 trillion suns. The escape velocity method provides yet another estimate. By studying how fast stars move in the outer halo, particularly hypervelocity stars ejected from the galactic center, astronomers can calculate the minimum mass required for the galaxy to keep them bound. The faster a star must move to escape, the more massive the galaxy must be. Using this technique, recent studies have found that the Milky Way's mass likely sits near the upper end of previous estimates. The Milky Way's mass distribution is not uniform. The central bulge and bar contain about 15% of the visible mass, while the thin and thick disks together make up another 70%. The remaining fraction resides in the stellar halo and globular clusters. Beyond that, the dark matter halo dominates, accounting for 9 out of every 10 kilograms of galactic mass. Interestingly, even though the Milky Way seems enormous, it is not among the most massive galaxies in the universe. The Andromeda galaxy, M31, is slightly more massive, containing around 1.5 trillion solar masses, while giant elliptical galaxies like M87 in the Virgo cluster can exceed 10 trillion solar masses. The Milky Way, however, sits comfortably above average, larger than most spirals, and perfectly balanced for a long-term stable structure. The question of the Milky Way's true mass is more than academic. It affects our understanding of nearly every galactic process. A heavier galaxy retains more gas and forms stars longer, while a lighter one loses material more easily. The Milky Way's mass also determines how strongly it interacts with nearby galaxies, and how soon it will collide with Andromeda. Even the number of satellite galaxies it can host depends on the total mass of its dark matter halo. Recent measurements using Gaia data suggest that the Milky Way's dark matter halo might be slightly asymmetric, perhaps stretched by its ongoing gravitational interaction with the Large Magellanic Cloud, LMC. Simulations indicate that this smaller galaxy could be dragging part of the halo along behind it, creating a wake, a kind of gravitational ripple that subtly distorts our galaxy's mass distribution. This discovery shows that even the Milky Way's weight is not static. It changes as galaxies interact and merge. The Milky Way is more than just the line of stars we see from Earth. It's a live system that is still growing, colliding, and changing over time. From the heart of Sagittarius A star to its ring of dark matter that can't be seen. It's all made up of stories that have been told for billions of years. And as the universe grows and shrinks, our galaxy will always remind us of how small we are in the grand scheme of things. Thanks for watching. If you liked this trip through space, please like, follow, and watch the next video. There's always more to find in the universe.